Welcome, everybody. Thank you for rejoining us for this session. It's going to be a very exciting session, with which we'll start with a keynote talk by Yonina Eldar. Then we'll have a few abstract talks, and we'll end with another keynote by Joseph Shaw. So we have the pleasure and honor to start this session with Professor Yonina Eldar from the Weizmann Institute of Science. Yonina is a world leader in the fields of compressed sensing and signal processing. She is the author of several books in this field, most notably the book of compressed sensing and the book Sampling Theory, Beyond Bandwidth Limited Systems. Just a few more words about Yonina before she starts. She received her BSc degree in physics in 1995 and the BSc degree in electrical engineering in the year following from the Tel Aviv University. She did her PhD in MIT in electrical engineering and computer science. And she's currently a professor in the Department of Mathematics and Computer Science at the Weizmann Institute of Science here in Israel. She won numerous awards of excellence in research. I would tell you the list, but I'd like to keep some time for the talk. It's a long and very impressive list. Recently, she was selected as one of the 50 most influential women in Israel. So just one to say one of these. She's also a visiting professor at MIT, at Duke University, at the Broad Institute, and she's a member of the Israeli Academy of Sciences and Humanities. She will talk to us today about from compressed sensing to deep learning. So Yonina, thank you very much for agreeing to give this keynote talk, and please start.
Well, thank you very, very much for the super kind introduction, exaggerated, but very kind, so thank you so much. And as I'm kind of sharing my screen, I'd like to thank Ori and Yoav and the organizers for really inviting me to give this talk here today. It's a true honor and pleasure, and of course, it would be much more fun in person, so hopefully that will happen soon as well. But meanwhile, I'm very grateful for the opportunity to do it virtually. All right, so let me begin. Does everybody see my screen? Okay, perfect, good. So what I want to talk about today are some ideas that we, and of course many others, have been working on, where our goal is to try and acquire and process signals and images using much less resources than what is used today. And we're going to try to do that by combining ideas of signal processing on the one hand, ideas of compressed sensing, but also what we call model-based deep learning. So deep learning that's based on models. And we'll see that this could lead to a variety of interesting new ways to sense information at high resolution, and also to interesting new technologies that we believe can have an impact on various different imaging applications, both medical applications and optical imaging. So as we know, today we live in a world where there's an enormous amount of data that's being generated. On the one hand, this is great, right? We have almost all the data we want. On the other hand, this creates a lot of different challenges. So it creates challenges in terms of power. The consumption of the IT sector is actually larger than some of the big countries. It creates a huge bottleneck in storage. So here, for example, we see one of 3 million data centers that store data worldwide. So obviously, we're taking up all this space just to store these bits. Processing it becomes very complicating, and communicating it becomes very complicated. So in a recent prediction by Cisco, they say that the mobile internet traffic will approach a zettabyte, which is 10 to the power 21. So I actually had to look that up, right? That's a ridiculously large number. And the question that we want to address today is, do we really need all of this data? So, these are crazy amounts of data, and is it actually needed? So why would we think it's not needed? So if we look at some of the applications that we've been working on, let's say medical imaging, which is a really good application, we're taking an enormous amount of data. And this, of course, means that we have huge machines, a lot of radiation, large scanning times. But at the end, we're not actually using all of this analog data. So if you think of ultrasound, for example, it's acquiring many, many channels. All of these channels are later projected down onto an image. So not all the data we're acquiring is actually being used. Another good example is smart cities or autonomous vehicles, which have become very popular. So we're using more and more sensors, right? LiDAR, radar, video, everything we possibly can. But then when we actually go ahead and make a decision, we're not using all of this information. Probably the most striking example are, of course, deep neural networks. So, we know today that networks could do amazing things. They could be used as very, very strong and sophisticated classifiers, but they do that after training on thousands or even millions of images, whereas a child could see, for example, a cat and a dog, maybe 2 examples of them, and then, immediately recognize a cat and a dog. So all of this is showing us that we're probably taking too much information, we're processing too much information. And the question is whether there's a way to acquire only what is actually needed for the specific task we're interested in. So this is a cool pop song by Judy Gorman, who sings about, being an analog girl in a digital world, which fits in really nicely with this talk. So, the signals we care about are physical signals, they're analog signals, but all of the processing is being done digitally. And to convert from analog to digital, we have an analog to digital converter, an ADC, which it takes samples at a time, and then it converts those samples to bits. Now, today, essentially all ADCs operate on the well-known Shannon-Nyquist theorem that say that we have to sample at least at twice the highest frequency, which is part of the reason that we have so much data. In fact, if we actually look at acquisition systems today, they're built in a very modular function. So they're built kind of block by block. So let me try to explain that. Suppose we want to take an ultrasound image, right? So we send a pulse, the pulse comes back, and then first we sample it, typically by following the Nyquist theorem. We then are going to quantize it, and the kind of rule of thumb that's used in quantization is that for every 6 dB we want an SNR, we have to add an additional bit. Only at that point, after we sampled and quantized, so we already invested almost all of our resources, do we start taking into account the task, right? Like, what do we actually want to do with this data? And for example, in ultrasound, it may be beamforming, and then we create our final image. So these blocks are optimized separately, right? Each one is kind of optimized based on its own individual input and output, irrespective of the overall task of the system. And this creates various bottlenecks in the system. So if we want to have large bandwidth, like when we want to communicate a lot of data, or when we want high resolution, this means by this modular blockwise design that we have to have very high rate samplers, very high rate quantizers. This leads to systems that consume a lot of power, take up a lot of space in terms of their hardware. They lead to a lot of data that has to be processed and transmitted. And in medical imaging, for example, this also translates to long scanning times and high radiation dosage. So at the end, this ADC that we kind of take for granted in the digital domain actually leads to bottlenecks in hardware, in data, and in power. So what do we suggest? What is the framework we suggest to try to overcome that? What we suggest is, first of all, designing systems in a holistic fashion. So rather than looking at them block by block, we want to do a joint design. And in this joint design, there's 2 main things that we're going to take into account. The first is any structure that we may have in the input or in the system itself. And the second is the actual task we're interested in. Okay, so the task is going to be taken into account throughout the design of the system. And even though here we're focusing on the sensing, the same ideas can also be used when we're doing deep learning, which is a purely digital problem. So even when we're just learning at when we're looking at data-driven methods, we're going to show at the end, if we have some time, that these same principles can also be used to develop deep learning methods that are model-based, are efficient, and also interpretable. So by doing this, by looking at this joint design, there's a variety of different benefits that we could get. So we can end up getting systems that are much smaller, very compact, have better quality. We could design joint systems on the same platform. So for example, we'll look at joint radar and communication systems. We could get very efficient sensing of wideband signals. We could get small devices with very high resolution. We'll see that we could get very low bit representations. And finally, we'll see some applications at the end to super resolution in both microscopy and ultrasound, and like we said, to interpretable deep networks. So that's kind of the main idea of what we're going to be proposing here today. And in terms of a more specific outline, we'll start by looking at the notion of structure. We'll then see how we can use that for reduced rate sampling, which is what we refer to as sampling. We'll see some applications to ultrasound and a little bit to radar. We'll then show more specifically how we could account for the task, and we'll see applications to super resolution in microscopy and ultrasound. And then we'll end with showing how we can use these same ideas in model-based learning and see some applications to image deep learning and again to super resolution. So this is the overall plan. All right, so let's begin by talking about structure. What type of structure do we expect to have in imaging? Now, when we talk about imaging systems, there's, of course, many different types of imaging modalities, and each one of them is going to have a different type of data structure. So, for example, if we think of spectral CT or hyperspectral imaging, we're imaging in different frequency bands. If we think of radar or ultrasound, or basically any time of flight system, we're basically using multiple antennas and multiple pulses to form an image. And if we think of optical imaging, there actually the main challenge is the lack of phase and, of course, the fact that we're resolution limited. So these are all very different examples that each one of them has kind of different structure and different constraints. But what we want to do is basically develop a unified framework that could take all of these different types of models into account and can lead to both rate reduction and super resolution. So in order to do that, let's just start by looking kind of at some of these examples one by one, and we'll see that this will lead to a general framework. So the first example we looked at was multispectral imaging or multispectral CT, where basically we're using several frequencies in order to form the image. Now, in fact, this is very similar to problems that you have in communication systems, where you have a multi-band model where you have a signal that is comprised of several bands. Each one of them is narrow, but they're spread over a wide frequency range. So this is a problem that we've studied a lot in the context of communication, and it's the same math that you would get in multispectral imaging. So in these problems, of course, I could still sample the signal at the Nyquist rate, but that would be wasteful because I'm not actually occupying the entire frequency range. So if I could develop a sampler that could take into account the fact that the spectrum is sparse, then I could sample at lower rates and get higher resolution. So this is an example in the frequency domain. If we think of time of flight imaging, which is in the time domain, then it's very similar to what we do in radar, basically. So we send a pulse, we get reflections from this pulse, and from each of the reflections, we want to basically know the time of arrival, which will tell us the distance to the target, and the amplitude, which will tell us the velocity. We get the same thing in ultrasound imaging, for example, where we send pulses through the probe, and again, by being able to trace out the times of arrival and the amplitude, we could plot a line in the image. So here the structure is actually pulses in time. And again, we want to be able to exploit that to use fewer samples and get better resolution. Now, in fact, the problem in ultrasound is more involved, and that's because the ultrasound environment is actually very noisy. So within the ultrasound probe, in order to combat the noise and get better resolution, we actually have hundreds of elements where each one of them is going to transmit and receive. And then in order to get better SNR, we want to beamform the data. So we do joint processing in all of the data. Basically, we align the data. So we introduce these small delays in time and then sum everything up. Now, of course, in practice, this is done in the digital domain. So we have to take enough samples so that we could do these delays on a digital grid. And this gives us another challenge. So it's not only the challenge of sampling, it's also the challenge of doing the beamforming or the processing on the digital grid at a low rate. So what we're going to see is that we can do this. And not only could we sample at a low rate, but we could also do compressed beamforming. We could do all of the processing at a low rate. And this gives us a variety of advantages. So it enables us to get rid of the machine and actually do everything very efficiently. For example, just on an iPhone, we'll show that later on. It allows us to do things quicker, so we could increase frame rate. We can enable 3D imaging, which today is limited by this bottleneck. And we'll see how this also leads to new technology like a remote wireless ultrasound probe. The final example I want to give is in optical imaging. Here, the main problem is that optical devices could only measure magnitude and not the phase. And we also know that optical microscopes are limited by the diffraction limit, so that we could only view details that are larger than half the wavelength used for illumination. So in practice, if we're trying to view these nanoholes through a microscope, what we're actually going to see is this blurry image, or in fact, mathematically, what we're seeing is just the low pass regime and only the magnitude of the low pass regime. Now, this in principle is a fully digital problem, right? So there's no analog to digital conversion here, but there's still the issue of exploiting structure to try and overcome both the loss of higher frequencies and the loss of the phase. So we can show that by exploiting, for example, the fact that this image is sparse, right? We only have a few elements that we're looking for. We could overcome both the loss of phase and the loss of high frequency content. Now, of course, we don't have to be limited to sparsity like in this simple image. We can have sparsity in more elaborate domains and exploit that to do sparse phase retrieval and also super resolution. So what we're going to see later on in the talk is that these notions of sparsity could also be used not only in these examples that people are familiar with from sparse recovery and compressed sensing, but also to develop very efficient and interpretable deep learning methods. So we could extend these notions to model-based learning as well. Okay, so we've seen a variety of different examples of structure that we would get in different imaging problems. And now the question is, how do we actually exploit that to reduce rates and to increase resolution? And that's what I want to talk about next, which leads to the sampling paradigm, which is a paradigm for low rate sampling. And all of these different examples you see here on the screen are different systems that we've built in the lab that follow this basic paradigm. So the first thing is to actually get a joint mathematical model. So we've seen, many different examples. They look quite different, but in practice, they all follow a joint model. And that helps, of course, to develop a general framework. And the model that we're going to look at is a model where we know that our signal lies in some low dimensional subspace, but we don't know a priori which subspace. So mathematically, this is called a union of subspaces model. It's a very simple model. But the nice thing about this model is that we can show that once we know that our signal lies in such a union, the sampling rate that is needed is the rate that's associated with a sum of two subspaces in the union, irrespective of the number of subspaces. So we could have a union of an uncountable number of subspaces, but the rate is only dictated by the sum of two. And this is really what paves the way to sub-Nyquist sampling. So this is kind of the mathematical framework. The question is, how do we achieve that in practice? And for that, we introduced the sampling hardware. So what this hardware does is that we could take our signal, we multiply it with a set by a set, or it could be a single periodic function. And the advantage of periodic functions is that we know that any signal that's periodic in time, in the frequency domain, it's going to look like a delta cone. And if we multiply in time, we're basically convolving in frequency. So what we're doing is we're taking our signal, and then by convolving it with the delta cone, we're replicating it, all the way to the right, all the way to the left, and summing everything up. And that's what gives us kind of this aliased version of the signal. We could then low pass it, so we only take a low pass regime of the signal and then sample at a low rate. So basically what we're doing in this sampling paradigm is that we're using analog pre-processing to alias the data. We're taking all of the options of subspaces and projecting them down on one low dimensional subspace. Since we're now on a low dimensional subspace, we could then sample that at a very low rate. And then after we've done this analog pre-processing, we could use ideas of compressed sensing to locate the correct subspace and recover the signal within the subspace. So this is a general paradigm that actually works for any union model. We could show that it has various forms of optimality. So from a mean squared error point of view, it will give you the smallest error over all methods that sample and a sub-Nyquist rate. From a communication point of view, we can show that it maximizes the capacity of the channel, so that not only does it always achieve the minimal rate, but it does it in an optimal way. Now, as I said, after we've done this sampling in the hardware point of view, we use ideas of compressed sampling to locate the correct subspace. And, I'm assuming people are familiar with compressed sensing, but just a very compressed version of compressed sensing is that in compressed sensing, we're basically interested in recovering vectors like this vector X that could be very long, but have only a small number of non-zero values, or a small number of non-zero values in an appropriate basis. And what compressed sensing theory tells us is that we can recover such sparse vectors from a small number of measurements as long as the measurement matrix is properly mixing all of the elements of X. So basically, the measurement matrix looks like a random matrix, and there's very efficient methods that will enable the recovery. So the basic compressed sensing was a linear theory. Over the years, we, and of course many others, have extended it in many ways. So one of the areas we've looked at a lot is extending it to nonlinear measurements for different problems in optics that involve nonlinear measurements, like sparse phase retrieval. We've looked at extending it to the case where we have multiple measurements, like an MRI, where we have multiple images. We've extended it to looking at tracking, like an ultrasound, where we're trying to track blood flow. Of course, we can look at sparsity in a statistical domain. And more recently, there's been a lot of work from various different groups, including our own, on replacing the standard compressed sensing recovery methods with methods based on deep learning. So there's various different extensions of this compressed sensing framework. Okay, so that tells us how we could sample at low rates. The only remaining missing point is how to quantize at low rates as well. And typically, different quantization results in the literature differentiate between sampling and quantization. So the quantization results, like rate distortion theory, are really all built on the fact that you've already sampled and now you want to quantize. But of course, what we're interested in is getting a complete system. So we want also the sampling to be at a low rate and also the quantization to be at a low rate. So for this, we basically extended results of information theory, and we were able to get kind of rate distortion theory for analog signals that will tell us for a given analog input, what is the minimal sampling rate and what is the minimum quantization rate we need in order to represent the signal. And what's interesting is that because anyways we have distortion due to quantization, right? Quantization always introduces distortion. Even if we don't know anything about the signal, we don't have to sample at the Nyquist rate because the Nyquist rate enables perfect recovery. But when we quantize, anyways, we're not going to get perfect recovery. So sampling at the Nyquist rate is always an overkill when you're quantizing with a small number of bits. So this joint rate distortion theory allows us to look at the trade-off between sampling and quantization and get the minimal rate, both in terms of sampling and in terms of quantization. The final component is actually achieving it. So we've spoken about how we achieve the sampling with existing hardware. Quantization is tricky because typically the rate distortion results that are available in the literature are achieved by vector quantizers that are complicated. So they're not actually easy to implement in hardware. What we wanted to look at is how we could do this using very simple scalar quantizers, because that's what hardware actually does. So, of course, in general, this is not possible, but what we can show is that, again, if we take the task into account, so if we look at the system as a joint design problem, and we allow ourselves a very interesting operation. So before we use these scalar quantizers, we look at using what's called analog combining. So this is very similar to what we do in compressed sensing. We basically multiply the signal with a matrix that looks like a random matrix, although it's not random, we design it, but it mixes all the elements of the input. And by this mixing, now we're not doing this for sparsity, we're doing this for quantization. But after mixing, it turns out that we could quantize with very simple scalar quantizers and still achieve the optimal rate distortion curves. So we're sampling at a low rate, we're quantizing at a low rate. We have this analog combiner that helps us both for sampling and for quantization. And by doing this joint design, we could sample and quantize at a low rate and still achieve the optimal performance we would have gotten from the theoretical curves that really assume that you're using more elaborate vector quantization methods. Okay, so we've talked about how to use this for ADC conversion. We've actually been looking at a variety of other applications. I won't go into that here, just mentioning it briefly on the slide. So we can use this for problems that have nothing to do with ADC conversion. So for example, we've been using these techniques for federated learning, which is a distributed learning problem. And we can use these efficient quantization methods in order to be able to reduce the communication load. We've been looking at using this for various multiple antenna systems where we basically do dilution in space. So instead of having to use a large antenna, we could use a small number of antenna elements, and many other different examples where, again, we're taking this notion of using a small number of elements and a small number of bits, not only for ADC conversion. Faster scanning, and here on the slide you see some of the systems we've developed in the lab based on these ideas. And of course, those of you interested in more of the mathematical details or the hardware details, you can find them in some of our books on this topic. Okay, so that was kind of a tour of, the overall theory behind it. I know it was rather quick, but hopefully you were able to kind of follow the main ideas. And what I want to show next are some applications to a variety of different areas, and hopefully convince you that despite this important and famous quote by Einstein, in theory and practice are the same, in practice they are not, that we could actually get this theory to work in practice. So the first application I want to show is to ultrasound imaging. And using these ideas, we can show that we can actually form images with only 4% of the data rate in every channel, and we can also dilute the number of channels. So this allows us to actually develop a new concept of an ultrasound imager, where instead of having a big system, we only have a probe. We do the sampling already directly in the probe because it's compact enough. We can actually do it in the probe. What comes out of the probe are just bits, okay? So the actual data comes out of the probe, goes into an iPhone or a tablet, and again, because this is all very low rate, we could recover in the tablet. So we basically get rid of the machine and have a very compact device. So what I'm going to show next is a demo of a system we've developed in our lab. This is Dr. Ayman Yarden, a cardiologist that we're working with, and here he's scanning one of my former students, Regev. Okay, so this is just used for power purposes. The data is coming out of to the local machine, to the remote machine via the cloud because the data rate is low enough, and also to the tablet. And now you see him scanning directly to the tablet. So even though we're using a very simple device, we're still getting a very high resolution, the same resolution you would get from one of the big machines. Now, the other nice thing about this is because the data is coming out directly from the probe, we actually have access to the original data, to the raw data, not just to the image. And now that we have the raw data, we can use model-based learning methods to actually get better images. And you see an example on the slide where by using a simple model-based learning, so we're training only from a single image, we can actually get better recovery than you would get from the standard beamforming techniques. So actually, at the Weizmann Institute, we started a clinical forum where we interact with a variety of different clinicians, and we've been looking at what else could we do now that we have access to this channel data that people didn't have access to before. So to me, this is kind of a nice application where basically based on new technology, we're actually getting access to clinical data that people didn't have access to before. Now, ultrasound is actually very similar to radar. So the same things we showed in ultrasound, we could do in radar or in any other time of flight imaging. So I won't go through this entire movie. All of these movies are available on my webpage for those of you who are interested. But basically, we could get similar effects also in radar. So we could try to break this trade-off between resolution and bandwidth. So we could use low bandwidth and still get good resolution. We could try to break the trade-off between dwelling time and Doppler resolution. So again, with smaller dwelling time, we could get very good Doppler resolution and of course the spatial resolution. So we do this again by employing this sampling framework. And this is the board or the radar system that we've developed in our lab. And what's nice is that even though we're sampling at very low rates, we could actually get very good resolution. So what we're doing is we're only using part of the frequency. We're not using the entire wide frequency regime, but with appropriate processing and everything is done in the compressed domain, we could combat both noise and clutter and get a very high resolution, as you're going to see in a second here on the screen. This also leads very nicely to what's called cognitive radar. So because now we don't need the entire spectrum, we can actually allow ourselves to live with other devices, for example, with other communication signals. So we could just look at where there's a communication signal and only use the available slots because now we don't need the entire frequency range. So these are different advantages we could get in the context of radar. Like I said, we can also reduce dwell time. We could reduce the number of spatial elements. I'm going to skip that in the interest of time, but those of you interested could see the movie online. We've been looking a lot recently at using this for autonomous vehicles because they're, having deep systems that could communicate, have both communication and radar at the same time is very important. So we have several demos that, again, you can see on my webpage, using this in the context of autonomous vehicles. We've looked a lot at getting good direction of arrival with small number of antenna elements. So again, this is very important in cars where you don't want to put too many antenna elements. And this is a short demo. Again, you could see it on my webpage where we use a very sparse array, so a small number of antenna elements. We're doing joint design of both radar and communication, and still we could get very high resolution in direction of arrival. So this is kind of a field experiment that we did at Weizmann. And again, you could take a closer look at this movie. You'll see how we could get very good direction of arrival, even though we're using a very small number of antenna elements. And we can also do joint radar on comm on the same system. So here we're showing it in the lab. The same system is what we use down in the field. But because we only need a small number of elements for radar and a small number of elements for communication, we could do them all together. Okay, so that kind of wraps up what we wanted to say about structure. I want to move on next very briefly and talk a little bit about tasks. So some of this we've seen already. What do we mean about tasks? So there's many cases where we're sampling signals, but we're not actually interested in the signals themselves. We're interested in some function of the signal. And the question is, if we take that function into account, could we reduce sampling rate? So we've seen that already we can do that, for example, for compressed beamforming. We've seen that we could do that for quantization. I want to talk about one last application that will also lead us into super resolution of power spectrum estimation. So there's many applications, for example, in array processing and even in imaging that we'll see later on. where we're sampling signals, but what we care about is only their second order statistics. And the question is, what is the rate at which you need to sample a signal to recover its second order statistics? And surprisingly, even though this sounds like a very basic problem, there aren't many results about that in the literature. So I'm not going to go here through the math. It's a little bit intricate because it's, of course, analog signals, but I do want to give some intuition. So why should we be able to reduce rate just because I'm trying to estimate covariance, for example? So to give some intuition, let's just think of a finite dimensional problem, although, of course, at the end, these are analog signals. So suppose I have some sampling set like you see over here, and I want to recover the signal. In general, the set is too sparse. It's not going to satisfy the Nyquist rate, and we're not going to be able to recover a band-limited signal from these samples. But now suppose I only want to estimate the covariance, and of course, we're assuming that the signal is stationary and ergodic, otherwise we can't talk about estimating its covariance. So when I care about the covariance, what I'm actually looking at are not the sampling points themselves. I'm actually looking at the differences between the sampling points, because we know that the covariance depends on the signal. Now, if I have n points over here, if I choose them correctly in the difference set, I can have n squared points. Okay, so I could get a factor of n in my sampling rate just because I only care about covariance. And now if you take this to infinity, you can see that you can actually create sampling sets that have a Berling density, meaning an average density of 0, but the Berling density of their difference set is going to go to infinity. So it means you can't recover the signal from the sampling sets, but you could, in fact, recover the covariance. Okay, so I'm going to skip the intricate mathematical details here, but hopefully that gives you the intuition of why, when I estimate covariance, I can actually get away with using far fewer samples. And what we're showing over here very quickly is just a demo where we use this to estimate the power spectrum of a signal that's sparse in the frequency domain. And like I said, we could use this for imaging applications where we're relying on multiple frequencies. So here in this particular application, we're looking at a signal that has a Nyquist rate of 6 gigahertz, and we're sampling it at only 6% of the Nyquist rate. And you can see at the top, you see the original signal. Here you see the alias spectrum. So, it just looked like a mess. But after using our recovery techniques, we could totally recover the signal, even though we've sampled at very low rates, and this is very robust to noise. It doesn't depend on any specific properties of the input signal. Okay, so what I want to do next is actually move into how we can use this for super resolution. So we know that, one of the limitations of optical microscopy is the Abbe's diffraction limit that says that we can't see details that are smaller than half the wavelength that we've used for illumination. Now, in 2014, the Nobel Prize in Chemistry went to this really amazing idea of super resolution using optical fluorescence microscopy, where the idea is to change the measurement process. So we allow, for these fluorophores to fluoresce, but we do it in such a way that to take one image, we take thousands of exposures, and in each exposure, only a small number of fluorophores are actually fluorescing. So then what we could do is we could basically localize them in each individual exposure and sum over all the frames to get one high resolution image. So this is a very clever idea. The difficulty, though, is that we get very good spatial resolution, but this is done now at the expense of temporal resolution, because to get a single image, we have to have thousands of frames. And of course, we assume that whatever we're imaging is not moving in between these frames. So this kind of precludes live cell imaging. But now if we go ahead and take a look at these images, these are basically brightness images. So instead of trying to estimate the signal, we can now think about estimating the brightness or the variance. And using our general sampling results, we know that instead of n exposures, we can now get a square root of n exposures and still get the same resolution. So if we translate it into this fluorescent microscopy idea, what we see here is comparing our method, which in this context we call it SPARCOM, super resolution correlation microscopy, with STORM, the method behind the Nobel Prize. And here we're using 2 orders of magnitude fewer frames, but still getting the same resolution or even better resolution. Here you can see a cavity that you don't see in the STORM image. Now, we can also take that one step further and introduce model-based learning ideas into this. And what that allows us to do is, from training from a single image, we could get even better resolution, but also we don't have to know any of the parameters of the system. So basically, this allows us to extend SPARCOM to a learned version where we don't have to know the PSF of the system. We don't have to know any system parameters. And training is done very easily from a single image and leads to very good resolution in both time and space. We've started some work with the group of Professor Villandaran at the Weizmann Institute to actually use this now for live cell imaging. So we're looking at the T cell receptors, and we started to get really exciting results where for the first time we can actually track the T cells in real time due to using these techniques. So the last application I want to mention is using a similar idea in ultrasound. Now, of course, in ultrasound, we can't inject fluorophores into the bloodstream, but what we can do instead is inject these microbubbles, this SonoView. And this is FDA approved. This is used actually to improve contrast. But what we want to use it for is to improve resolution. So basically, we're using the same ideas that we're using in microscopy. And this leads to very good resolution. So in this context, we call the method sushi. So the first time I presented this method actually at an ultrasound conference, someone got up and said that it was a very fishy method. But it does look fishy because you get very good depiction of the blood vessels, as you see over here, just by using these super resolution ideas. Okay, so this takes us to the end of the talk. I think I'm still basically on time, so this is the last part of the talk on model-based deep learning. So how we could take these same ideas of exploiting models, doing joint design, and using them in totally digital problems that have nothing to do with sampling, and in particular using them in these contexts of deep learning. So, of course, everyone is aware of the amazing results we could get with deep networks. I won't say too much about that. Definitely in imaging, that's one of the areas where people have used deep networks the most. But really, the areas that we get the best performance from deep networks are areas that were originally hard to tackle with models. So to begin with, we didn't necessarily have good models for these types of problems. But there are, of course, many challenges associated with deep learning. So we need very large training sets. The methods are typically not very interpretable. It's not clear how well they generalize to new methods. It's not clear how robust they are. And basically, sometimes it feels like you're just, mixing the pile of everything you have. And if it doesn't look right, you just continue to mix and something else will come out. But if you think of problems that we're interested in, so medical imaging or radar imaging, here mistakes are very costly, so you can't allow yourself to have mistakes. You want things to be interpretable, and you actually have a lot of knowledge. So it kind of seems wasteful not to use that knowledge. Now, if we look at the other extreme of signal processing or model-based signal processing, because signal processing is kind of by definition model-based, it relies heavily on modeling. The nice thing is that we could easily incorporate, anything we know about the problem, domain knowledge, structure. It typically allows inference from a small amount of data, and also we could actually analyze the results that we get. However, of course, it relies heavily on knowing the model, which we may not know, and the inference could be very slow, especially if the models are complicated. So what we've been looking at in recent years are different ways of trying to combine kind of the best of both of these worlds. So how could we do that? So to explain how we attempt to do that, I want to kind of give, a bird's eye view of how we could think about signal processing versus learning. So in signal processing, typically, you're going to have some input. You have a single input, so we'll call it Y. You're interested in some output X, so maybe Y is your noisy image and X is your denoised image. And you're going to have some function that relates them. So you assume that Y is approximately equal to some G of X that you know in advance. And then you're going to come up with some metric. So it could be, some norm function or some regularized norm function that you want to optimize. And, typically it's not going to have a closed form solution. So you'll have some iterative method to solve it. And the iterative method will typically look like something like this. You'll have some pre-processing. You'll then have the iteration step, where the iteration step has some generic steps and some steps that depend on the model that you're assuming. And then you'll have some final post-processing that will give you your output. Now, if you think of deep learning, of course, the picture is totally different. So in supervised deep learning, which I'm going to be focusing on here, you have many paired inputs and outputs. You have some generic fixed network that has nothing to do with your problem in general. And now you're going to use those inputs and outputs to train the weights in this network. And then when a new input comes in, you're going to hope that miraculously it's going to output the correct output. So now the question is, how do we marry these two? And, there's many ways you could think about doing that. I want to focus here on two of the methods that we've been looking at a lot in our lab. So the first method is what's called deep unfolding, and I'll explain that in the next slide, where basically you're going to take these iterative techniques, but insert learning into them. So I'll discuss that on the next slide. And then the second method is that you start actually not from the optimization problem, but from the end algorithm. You keep the algorithm, but anytime there's a block that depends on the model, you just replace that specific block with a deep network. And it's actually usually going to be pretty shallow because it's only used for a specific block, not for end-to-end learning. And this is what we call hybrid algorithms. So these are kind of the two methods that we've been using in our lab. And let me elaborate a little bit further on both of them. So the first one, deep unfolding, goes back to a really beautiful paper of Gregor and Lacoon from about a decade ago, which used this for sparse recovery. And actually, for many years, people really don't look at it too much. But in recent years, there's been a lot of interest, particularly in the signal processing community, at these unrolling methods. So those of you interested, we have a recent review that we wrote on this topic that hopefully could give you more details. So the basic idea is really simple and very clever. So, we take this iterative algorithm that we illustrated before. Basically, what you do is you write down a fixed number of iterations. So let's say you say, I'm going to look at 10 iterations of this iterative algorithm. So up to this point, there's no learning. But then in the final point, what you're going to do is that in each one of these iterations, there's parameters that depend on the model that you don't know, and you're going to learn them from training data. So basically, the architecture itself comes from the underlying optimization algorithm, but then the variables that you don't know, you learn from data. And this is what's known as algorithm unrolling. So like I said, in the original paper, they looked at sparse recovery. We and many others have extended this in a variety of different ways. The method, like I said, actually starts from the end. So unrolling starts from the optimization problem, from the formulation. The second method is good for problems where we don't necessarily have a very clean optimization formulation, but we have a very good method. And we use this in particular in our lab a lot for communication, because communication networks, there's many solutions that people have developed over the years that work very well in practice. They're not necessarily direct solutions to opt itself. And anytime there's a block that depends on something we don't know, we just replace that specific block. And again, those of you interested, we have a recent review that we wrote on this method, particularly for communication systems. Okay, so let's go back to unrolling. That's the main method that we use in imaging problems. So the first type of results we looked at was together with the group of Vishal Manga. We've looked at this just for simple deblurring, okay, which of course many people have looked at, but we wanted to get a simple interpretable method for unrolling. And here what we did is we looked at an optimization problem that we formulate in the gradient domain. So let me give you, just very briefly a little bit of the details. So we assume that we don't know the PSF, and of course, we don't know the underlying image. We basically set up a least squares problem in a field optimization problem that would give you kind of a standard. We unroll it, we write down a fence and learn these unknown parameters from the data. The surpassing state-of-the-art results, we use a very small training set and get better results than all of the competing methods out there that are based on more generic deep learning, use much larger training sets, and still we get better resolution, and we have a very simple interpretable method with a very small number of layers. Like I said, this slide I've already showed, we use this for model-based deep learning. So basically we took Sparcom, we unrolled it, and all training is done from a single image. So this is very efficient. It gives you a very convenient 10-layer interpretable network that's trained on a single image that surpasses, all the deep learning methods out there for super resolution microscopy. We've used this for super resolution in ultrasound. So I've mentioned this before as well. What I want to show in ultrasound is just a clinical study that we've done recently, which we were very excited about. So basically, we took this method. It's very simple. Here, we don't even train from any real data, okay? Because the doctors are very nervous about training. They don't want us to make up features that don't exist. We did training offline from a simulator. So basically, it's not a trained system. And again, it's very simple. It has 10 layers, so it's a very convenient network. And we did a study in Bellington Hospital together with a group of Dr. Ova Grubstein, who leads the breast cancer center there. And basically, we took images of 20 patients with breast cancer, and I'm just going to show you two of the images. So these are two of the images we worked on. This is what you see in standard ultrasound. So I'm going to show both of them. In both of them, you can see a tumor, but they look the same. It's just a black hole. You can't know what's in that tumor. On the left, you see kind of competing methods. So let's leave that for now. But on the right, you see what we get from our technique. So it's very simple, and you see that you could actually get the vascularization within the lesion, which is what's important clinically. differently. So here you see a fibroadenoma, which is a benign tumor. Here you see, unfortunately, a malignant tumor, and you see that the breast characterization is very, very different. And from the doctor's point of view, this allows them to detect that this was actually a malignant tumor and this was a benign tumor. So these methods are super effective. Here, we're not training on any real images. All training was done on simulations. Another thing that we could do with these type of techniques is separation. So for example, in ultrasound, often you want to separate between the tissue, which is basically clutter, and the blood flow, which has like this sparse nature. So what we did here is we set this up as a low rank plus sparse decomposition and then used in an enrolling framework. Actually here, this method was from 2 years ago before COVID. And at the time we called the method Corona, without predicting COVID, convolutional robust principal component analysis. And we laughed that the method became viral. But anyway, it's very effective at separation. We've used similar ideas for radar and other problems where we want to have separation. So let me skip the math. Basically, we just set up this robust PCA problem, unfold the networks, learn them from data, and it gives us this very good separation. So let me just end. I won't go into detail here by saying that we can use similar techniques for communication systems. This is a conference about imaging, so I won't go into it, but I'm just going to mention it. We've used this for a variety of different communication problems as well. And finally, to end with COVID, hopefully the end of COVID as well. We've used this in the past year. We've worked with several clinical centers through our clinical forum. We do a lot of clinical work in the lab. We've worked with several centers to try and see how we can use these techniques to help with different COVID problems. And particularly, we've been focusing on doing detection, COVID detection and monitoring from both X-ray and ultrasound. And using these model-based methods, we were able to get very good detection, so over 90% detection, which surpasses the methods out there. And the data here, we had a large data set where we looked at different hospitals, so we can show that it's pretty robust over different machines, different centers, different patients, etc. And as I said, we've been applying this also to ultrasound as well. So with that, I'll wrap up. What we tried to present is how we could get, efficient and interpretable methods for sensing and for learning from data. And we do that by designing systems in a holistic fashion, trying to take everything into account. We've seen that this leads to interesting new mathematical theorems. It potentially leads to interesting new engineering devices. And at least to me, one of the exciting things that we're trying to focus on now is to see how we can use this for interesting scientific and clinical breakthroughs now that we could see things that we couldn't see before. So let me just end by saying that I've skipped all the mathematical details. Those of you interested could find them in our books and on our webpage. None of this would have been possible without my amazing team and students that I've had the pleasure and honor to be working with over the years. And of course, my amazing collaborators who've contributed to different parts of the work that I presented. And thank you very much for your attention.
Thank you very much, Yonina, for this fascinating talk. We have a few minutes for question, and I'd like to start with one question. You talked about your work span many fields, ultrasound, radar, optical imaging, and at least in the compressed sensing, still not in the learning approaches. You have to base on some sparsity in some domain. And could you comment on the sparsity domain or the differences or the similarities between, let's say, ultrasound and radar, or perhaps even optics? Are there any similarities, or are they completely different? Or
Yeah, okay, very good question, very good question. So the traditional compressed sensing does, in fact, rely on some sort of sparsity. I do just want to emphasize that a lot of what we're doing is not relying on sparsity. So the task-based ideas, actually, you don't need sparsity at all. So the ideas based on covariance or based on quantization, those don't require sparsity. But I think also when we think about sparsity, sparsity was the traditional compressed sensing. Today, we think about it more as structure, even if we don't know the structure. So sometimes in radar is actually a good classic example of structure, because the structure is just the fact that we have a small number of pulses. So that's kind of the sparsity we have in the problem. But in ultrasound, for example, it's actually more involved because there's so much speckle and noise. When you look at the signals, you actually don't see those pulses. But still there's structure, right? Because we know that we could decompose the signal into, a component based on speckle and a component based on pulses. So I think about it more, with this more modern take on it, looking retrospectively, more having some underlying structure, and it could be a sum of several types of structure. Now, if we know how to write it down mathematically, like if I could really say, you know, it's this plus this plus this plus that, then we can use more standard techniques. When we don't actually know how to write it down, we know it's there, but it's kind of hard to really piece it up, then the learning-based methods that are based on modeling are more effective. So I think radar and ultrasound share some similarity in the sense that they're based on pulses and their noise is kind of based on clutter. Optical images are very, very different. They actually have totally different type of structure. There, the difficulty mainly, again, is losing the resolution and the phase. And the structure really depends on what you're imaging. It's not an inherent part of the system. So in optics, in our work, we tend to rely less on sparsity because it's not an inherent part of the system, and actually try to rely more on the mechanism of the optical device. Whereas in radar and ultrasound, we rely more on the sparsity because it's an inherent part of the imaging system and not so much on the device. So I think that would be like the major difference between them.
Okay, thanks very much. Very interesting. We have one other question from the audience. Wonderful talk! Exclamation mark. There is always a trade-off. There is always a trade-off between very precise physics of the image formation and simple neural networks models, and the simple physics model and collecting a lot of data. How does one choose which path to take?
Yeah, really good question. So thank you for that. So, you know, first of all, of course, there's no decisive answer. I think that's kind of ongoing work. But what we're trying to promote in our lab are these model-based frameworks, which we found are quite effective in trying to resolve that. So what we do in these model-based frameworks is that we actually start with the underlying physics, but a simplified version of it. So we don't take, you know, the most elaborate physical model because then it becomes too complicated. So we start with the physical model, we unroll it. So basically we get, you know, a deep network, but not more than 10 layers. So it's like a shallow deep network. And then we learn the missing parameters. And what that kind of allows you to do is that in the learning stage, we're not only compensating for parameters we don't know, we're actually also compensating for mismatches in the model. So if we start with the simple model and then learn, it's effectively as if we started with a more complicated nonlinear model. So we found in our lab that that's a good way to kind of compromise between, you know, models on the one hand using knowledge, on the other hand, you know, allowing for some mismodeling. The training in all of the examples I've shown, training is always done on a very small training set. So in the optical example, we trained on a single image. In ultrasound, we actually didn't train at all. In deblurring, we trained on a few hundred images, but typically in deblurring, people train on, you know, tens of thousands of images. So the training is always done on a very small training set in these model-based frameworks. And in that sense, we try to kind of compromise these different constraints. I do have to say that what's lacking, and if there's anyone interested, I'd be super happy to talk about this offline. And we're starting to work on this, but it's very, very challenging, is being able to quantify that analytically. So, you know, I really like building systems. I really like having methods that work. I also really like proving them. So I am a mathematician at heart. And, you know, having things that work but don't have a proof is, at least for me, unsettling. So we are trying to work on actually proving what I just said. Of course, like anything in deep learning, proving results is complicated. You know, we have beginnings of works. Hopefully one day I'll be able to share a complete picture, but that is actually quite challenging. But empirically, I have to say that across all of the examples that we've looked at, and I've showed quite a few that are very, very different, the method appears to be very, very able in practice to kind of trade off those different constraints.
Okay, thanks very much. Perhaps just one quick question. So you mentioned mathematical bounds, and you mentioned also on the way a nonlinear compressed sensing or compressed sensing for nonlinear problems. And, you know, phase retrieval is one of these annoying problems that it's not clear if there are any proof for convergence for the standard algorithms. So are there any mathematical proofs for this use of compressed sensing in these nonlinear sort of, let's say, phase retrieval problems?
Yeah, okay, good. So thank you for that, because I didn't have time to elaborate on that. Yeah, so that's actually work we've done several years ago with a variety of different people, with Emil Beck on the optimization side and Moti group on the Moti Sekev's group on the optical side. So there's a variety of cases that we could actually prove. You know, not everything, of course. We could prove convergence of the algorithm. We could even prove convergence of FineUp, actually, that wasn't proven before. So that's kind of like a you know, a special case of with sparsity, you could get as a special case different convergence results on FineUp. So from an optimization point of view, we could actually prove convergence in those cases. from a point of view of convergence of the result, like showing that there's uniqueness, etc., that's more intricate. So we could prove uniqueness under several different types of constraints, not generically for any type of structure or any type of sparsity, but for specific classes of functions, we were able to prove both uniqueness and convergence of the underlying algorithms, but not the standard algorithms people use. So they're like modified versions of the standard algorithms.
Okay, Yonina, we are out of time, so thank you very much.
Well, thank you. And if anybody found anything interesting and wants to chat more, I'm really, really happy to chat offline. And hopefully, by next year, we could chat online as well. Not online, in person.
In person, yeah, that would be innovative. Yes, so thanks very much.
Thank you.
Everyone here, I invite you to stay. We have a few paper talks now, and following that, another keynote talk by Professor Joseph Shaw. So thanks very much.
Okay, thank you.
Hello, everyone. Welcome to session Monday D of the ICCP conference. Thank you for being here. I am Vivek Bhuminathan, and I'll be the chair for this session. In this session, we have 4 exciting talks, 2 of which are ICCP papers, and 2 of the other are physics optics abstract talk. We can get started. Please, as the video of the talk plays, please post your questions in the comments. All right. The first paper of the session is an ICCP paper, and it's titled Real-Time Light Field 3D Microscopy via Sparsity-Driven Learned Deconvolution by Josue, Zeguan, Panagiotis, Paolo, Burko, and Edward and Tobias. The video presentation is going to be done by Josue. Let's watch the video for the talk.
Good day. My name is Josué Page Vizcaíno, and I'm presenting to you our work accepted to ICCP 2021 named Real-Time Light Field 3D Microscopy via Sparsity-Driven Learned Deconvolution. I hope you enjoy. We are looking for a technique that enables volumetric real-time imaging of sparse events in live specimens, such as neural activity in zebrafish and C. elegans. In this work, I'll guide you on how we approach these challenges. For this, we need first a microscope capable of imaging live specimens that is real-time, possibly scanless, that can perform functional volumetric imaging, and affordable. Secondly, we have the computational requirements, where we would like to reconstruct only the sparse interesting signals, such as the neural activity, and that we can perform real-time 3D imaging, if possible with a small amount of data and a reduced storage. Let's start by clarifying the microscope we used. A conventional fluorescence microscope captures 2D information of a sample. If we would like to acquire 3D information in a scanless setting, we could aim for a light field microscope. In this case, we use the extended field of view light field microscope, where we have an extra lens that allows the camera and the microlens array to access the Fourier information of the sample. This type of microscope captures not only spatial information, but also angular information that can later be recovered into a 3D volume. Let's clarify this microscope with an example. If we have a sample that we like to visualize, a light field image would look something like this, where each lens captures a different point of view of the sample. Here we can see the neural activity of the fish in real time. An advantage of this type of microscopes is that you only have to capture one image, and from this single image you can recover then the 3D information. Now we can jump into the computational requirements, where we would like to filter only the interesting signals. An advantage of the neural activity is that it's sparse in time and sparse in space, meaning that across many frames of a video of a fish, the neurons are not going to always be on. They turn on and off in their own patterns. So, if we have a sequence of images, we need an algorithm that can compute the low rank component and the sparse component. The sparse component will be sparse in time and space, showing only the neural activity. This can be achieved through several methods. For example, the work of Yonina Eldar uses a loss function that minimizes the nuclear norm of the low rank component L and the L1 norm of the sparse component, subject to that the sum of L plus S is equal to the raw images. Furthermore, the method of Herrera et al., originally created for finance, optimizes only the low rank component and computes the sparse component through a simple subtraction. The first method optimizes the loss function with the augmented Lagrangian multiplier method, as it is a constraint optimization problem. It takes around 1 second to compute the sparse component of 3 images. However, in the original work, they use a stack of 1000 images, which would take around 12 hours to compute. We decided to try the second method, where we introduced a neural network operator with parameters theta that takes the raw input and computes a low-rank stack out of it. Our loss function also uses the operator gamma, which clamps the singular values above a given threshold iteratively, penalizing high-rank solutions. So, we take a stack of images at different time points, run it through 2 convolutional layers to compute the low-rank component, then compute the sparse component out of it with this equation. This approach is trained fully unsupervised and can process a sample of 3 images in 5 milliseconds, achieving 200 frames per second. We consider that convolutional layers are very well suited for this task, as they naturally blur the inputs and produce already a low-rank approximation of the input. The results talk by themselves. The recovered sparse component shows in a cleaner and without all the haze the neural activity of the sample. It is important to mention that this technique can be applied to many other types of microscopes and samples. This activity would otherwise be very hard to extract from the original images. So, now we have a way of using the images from a microscope to compute a sparse series of images. The SD algorithm is the work from Yonina et al. Previously mentioned, which takes 1000 milliseconds to compute the sparse series. The SLNet is our proposed method. Now we can jump into the real-time 3D reconstruction part. Usually, this is performed with 3D deconvolution, with the Richardson-Lucy method, for instance, and it takes around 45 seconds per volume, being far from real time. In our work, we use the images generated by the SLNet already trained and crop the images from each lenslet. Then we stack those images in the channel dimension and use a 2D unit to compute the volume in a sparse matter. This takes around 25 milliseconds per volume, making it quite fast and enough for real time. How do we train this? Once again, first we train the SLNet in an unsupervised matter with 100 images. Then we generate a 3D dataset by deconvolving these sparse images and generating these 3D volumes, and use that to train the XLFMNet in a supervised matter. Now, to visualize the impact of the method, we can see on the left the 3D reconstruction of the raw images with deconvolution, and on the right the proposed method. If one is interested in the neural activity, it's quite clear that on the right the neural activity is much visible and allows us to measure the neurons in a cleaner fashion. An important requirement when using neural networks with biological samples is data fidelity when using them with unobserved samples. We tested this fidelity by training the networks with a single fish and testing it on 3 other fish at different life stages and staining. Also, we tested them in microspheres. For this test, we selected some active neurons on each fish and compared their temporal activity. We compared the 3D convolved results of the raw image against the SDLFM, which is the method of Yonina Eldar, the 3D deconvolution of the SLNet sparse results, and the full proposed method, SLNet plus XLFMNet, showing a very high data fidelity. To conclude, in this work, we presented a real-time, unsupervised, sparse decomposition technique applicable to other microscopes and sample types. Also, a 3D real-time approach which enables closed-loop experiments, where depending on the neural reaction, further stimuli is provided to the fish, such as smell, light, etc., allowing a more complex understanding of the neural systems. However, we leave this to future work. Thank you very much and wish you a good day.
Awesome. Thank you for the talk and the amazing results in the presentation. Let's now for the Q&A session. Here's a question for you, Jose. So you have this unsupervised sparse decomposition network, which runs really fast. What is the stopping criteria for it? When do you decide this is sufficient sparsity?
Well, there is a metric where you can add the sparse part and the low rank part and subtract that from the original image. And pretty much you're trying to minimize this error. And this is mainly the stopping point. Eventually it converges to something and it stays like that. But
okay.
That's pretty much it.
Okay, thank you. And one more question. What stage does this method help in reducing noise in the final 3D reconstruction? From the sparsity to the 3D reconstruction, I see noise reduction. At what stage does that happen?
Well, if you think about noise, it is sparse in space and in time. I don't have a good answer for this on the top of my mind.
Okay, I mean, that's good. I mean, maybe it's something in the future to analyze.
Yes, it's not something that I noticed that the images are super noisy, but yeah, I'll think about it.
Okay. One last question. How does your approach compare to, say, L1 optimization techniques in terms of quality?
You mean using an L1 loss?
Mm-hmm.
Well, we do use a L1 loss for the sparsity, but just using the L1 loss, we did not compare against that. So it's hard to comment on that one.
Okay.
But in this case, we are optimizing the low rankness of the images. We're not directly optimizing the sparsity. So we could do a indirect comparison, perhaps.
Yeah, for sure. Awesome.
But, I think the method can be used with any microscopy images, and it's a matter of giving it a try.
Okay. Thank you, Jose. Thank you for answering the questions.
Thank you.
Thank you. And now we can move on to the next talk. And so just to briefly, so this first paper was an ICCP accepted paper. The next talk is different from previous years of ICCP. So next talk is called a physics optics abstract talk. And this was basically to integrate deeply the physicists into our community. So from this year, ICCP is accepting oral abstracts, which are going to be integrated into the program. And along with the paper presentations, there's also going to be physics optics abstract talk involved. So the next paper is one of them. And these talks are basically chosen based on the abstracts using our newly formed optics board. So we formed a new board to complete new board to judge all these abstracts so that we can incorporate them into our conference. So given that brief overview of like what a physics optics abstract talk is, that's going to be the next one. So the second paper, the physics optics abstract talk, is titled Fundamental Bounds on the Precision of Classical Phase Microscopes. And the presenter is going to be Jonathan, and the rest of the authors are Dorian, Dante, and Thomas. So let's watch the video for the presentation.
Hi everyone, I'm Jonathan Dong, and I'm glad to present you our work on fundamental bounds on the precision of phase microscopes. This work has been done in collaboration with Dorian Boucher, Dante Maestre, and Thomas Hufman between Utrecht, Paris, and Vienna. In phase microscopy, contrast in the images comes from differences in refractive indices. This is especially useful for biological imaging, as we can see that cells are fairly transparent, but their details are revealed in phase microscopy. This enables to monitor cells in a culture medium as they grow or divide. Compared to other techniques in microscopy, it presents the advantage of being relatively simple to implement and do not require a specific marker. Thus, this label-free technique is an essential tool in biomedical imaging. However, cameras record intensities, and as such, phase differences need to be translated into intensity contrast. This is done using interferometric schemes, typically with an external or internal reference, as we will describe next. Here is a simplified drawing of a phase microscope with an external reference. The sample on the left imprints a certain phase pattern on the wavefront that we convert to intensity fluctuations by introducing an external reference and collecting the interference patterns on the camera. The presented imaging scheme corresponds to Fresnel holography, and several variants have been proposed. For example, off-axis holography uses tilted reference beam and analyzes the resulting interference fringes, while phase stepping implements an equivalent method by dephasing the reference by regular increments. On the other hand, the Zernike phase contrast microscope, or PCM, is based on an internal reference strategy. It has the benefit of being more robust to mechanical instabilities, as the phase of the reference and the object wave need to be constant in time. In this Zernike phase microscope, a pi/2 phase shift is introduced at the origin of the Fourier space, which creates a dephased reference wave. Note that recent implementations use a partially coherent illumination and an annular faceplate in Fourier space, but we'll consider this simplified, fully coherent case. Other techniques for quantitative phase imaging have also been proposed, such as photography, differential phase contrast, and many other ones. They typically capture multiple images and reconstruct the phase computationally. These more complicated schemes still fit our framework, as they can be modeled by a linear system, But for the simplicity of the following discussion, we will focus on the first two cases with an external reference or an internal reference scheme. We would like to point out two challenges for these interferometric schemes. First, there is an optimal range for phase sensitivity, and we will show that they are designed for weak phase objects. Second, all measurements are ultimately limited by shot noise, because a finite number of photons interact with the sample and arrive on the detector. For the first challenge, when the sample presents strong phase variations, we can introduce wavefront shaping with a spatial light modulator or SLM. This allows us to put ourselves in the weak phase approximation again, and we will show how this increases the sensitivity of the microscope. This SLM can be introduced on the internal reference or after the sample for the internal reference case. The shot noise limit will be the subject of this study. It arises in high sensitivity measurements when the number of detected photons is limited due to photon damage or short exposure time. It is in this setting that we propose a statistical analysis on the precision of phase estimation to study photon-efficient microscopes. We will use the Kramer-Rao formalism that we will detail later. Note that such type of analysis has already been proven to be useful in localization microscopy, either 3D with PSF engineering or the Miflex technique, as well as the estimation of arbitrary parameters in the scattering regime. Here are the main elements of any Kramer-Rao analysis. We have a set of parameters to estimate. For example, the phase image we want to recover here. Measurements on the camera are given by the imaging system following a Poisson distribution, as well in the shot noise limit. We then quantify the information in the noisy measurements with the Fisher information matrix. More photons decrease shot noise and increase this Fisher information. Finally, the Kramer-Rao bounds correspond to the minimal variance of any unbiased estimator. It provides a lower bound on the precision of our estimation, limited by shot noise. Of course, this analysis depends on the microscope at hand and is typically done for each imaging application. In this work, we derive fundamental bounds on the precision of phase estimation. We call them fundamental because they are valid for any linear classical phase microscope. We will thus start by the statement of this fundamental bound and how to saturate it. These conditions for saturation will be important as they allow us to compare the different phase microscopes to this bound. This comparison study will be illustrated with numerical results on strong phase objects. Let's start by defining the different mathematical objects for our generic phase microscope. We start with the object, which is a complex valued vector of dimension d. The unknown phases, phi j, are the parameters we want to estimate. The amplitudes, squared, correspond to the energy, and thus to the number of photons. Our imaging system will be modeled by a generic linear operator h. This describes the linearity of wave propagation, which is the case in a vast range of imaging systems, as long as they do not rely on nonlinear optical processes. The measured intensities are the modulus square of the electric field after propagation. Note that we add the possibility to have an external reference, EREF. This intensity IK corresponds to the expected number of photons arriving on the camera. The actual measurement on the camera is shot noise limited and thus follows a Poisson distribution with IK for expectation value. Our main result is the following. For any imaging system, the Fisher information for phase estimation is bounded by 4 times the number of incident photons, which means that the variance of any estimation is larger than the inverse of 4 times nj. We thus obtain the intuitive result that the more photons are sent, the more precise the measurements are. But this result is valid for any linear classical imaging system, and as such describes a fundamental bound which cannot be beaten by any other classical imaging scheme. The full derivation of this result is presented in our recent paper, and we can ask ourselves how to saturate these bounds. which means that we are looking for which imaging schemes are photon efficient. There are 4 conditions to reach this bound. First, the existence of a minimum variance unbiased estimator. This is not automatic, but should apply in our case. Then, the Fisher information matrix needs to be diagonal, with no crosstalk between different phase values to estimate, which is also the case in an imaging system. Furthermore, the optical system has to be lossless, and in other words, the operator H, characterizing the imaging geometry, has to be unitary. Finally, and most interestingly, there is a phase matching condition to be fulfilled. In the simpler case, where H is equal to identity, and the reference much stronger than the object, this boils down to a simple relation between reference and object phases. They need to be dephased by pi/2, which is the case in phase contrast microscopy for weak phase objects, as the reference typically has a constant pi/2 phase. But note that when the object gets stronger, then it is impossible with a constant phase reference to saturate this phase matching condition. We now show numerical results on the camera bound of different phase microscopes for a strong phase object. We start with an external reference, with the cameraman test image for the phase and the Gaussian envelope on the amplitude. In A, we have the typical image collected on the camera, and the associated map of camera bounds is presented in B. We observe very high value of the camera bound in the regions in yellow, which means that for these parts of the image, the precision of phase estimation is quite poor. With phase stepping interferometry instead of a single image, one can compensate this effect of a strong object. However, if a wavefront shaping strategy is adopted, we can get even better precision and saturate the fundamental bound based on a single image. With an internal reference, the same conclusions can more or less be reproduced. The camera bound map of a conventional phase contrast microscope presents many regions with poor phase sensitivity due to the strong phase of our object. This is also the case for phase stepping interferometry in C, which differs here compared to the external reference case, probably due to some crosstalk in this internal reference scheme. With wavefront shaping and lo-fi, we are able to still saturate the fundamental bound in sharp contrast with B and C. Hence, this wavefront shaping technique increases the sensitivity of phase estimation, both with an external and internal reference scheme. To conclude, we have discussed a fundamental bound on the precision of classical phase microscopes. In particular, we have shown how wavefront shaping and the lo-fi technique allows to stay in the optimal sensitivity range. Such a framework has been useful to compare different imaging schemes, showing, for example, that the Zernike phase contrast microscope does not perform well for quantitative phase imaging with strong phase objects. On a more practical side, this study would be useful for practitioners as they could assess whether a particular experiment is operated at the short noise limit. And finally, we would like to mention that a fundamental bound on amplitude estimation can also be found in our paper, which may be useful for certain applications, such as mass photometry. With that, I would like to thank you for your attention, and feel free to write us your questions to continue the discussion.
Awesome. Thanks for the talk. And it's great to see work that's analyzing fundamental bounds for different, especially phase microscopes. So here's my question. So you showed fundamental bounds for classical phase microscopes. So what other techniques excludes classical approach? Like what would you consider as a non-classical approach?
So it's a very interesting question to see the limits and the assumptions of this work. So we suppose that we had a shot noise, so like a thermal noise. I'm not that much into quantum mechanics, but it's like whenever you have like entangled photons, maybe it's possible to break these bounds, because, for example, there are a lot of people using squeezed states for metrology, for example, for quantum metrology. So this would help us break these bounds.
Okay, thank you. And so a few questions from YouTube. Orikats is asking, saying, very interesting talk. Could you comment on how to find the optimal reference field for a given object? Is it something that needs to be adaptively found using multiple measurements?
Yeah, so how to find a good initial guess to do the wavefront shaping to stay in the optimal range is still like, there are a lot of possibilities and not very like clear how to do it. But for example, any, it really depends on the application. Like any, even if it's not photon efficient, like we do a digital holography, for example, we find an approximate guess, and then we will be close to the optimal range to follow dynamics, for example. So it depends on the application. But yes, there needs to be a calibration step.
Okay, thank you. And one last question. For the wavefront shaping technique, typically how many measurements are used in your experiments?
For the wavefront shaping, I'm not sure what it means. So if it's to measure the phase without an initial guess, without the weak object approximation, typically it's 4, for example, in a SLIM. We do 0, pi over 2, pi, 3 pi over 2 phase shifts, and then we use that to reconstruct the phase. Or when we are in the weak phase approximation, just one image is enough. We're just looking at the contrast in our image, and we have the phase out of this image.
Okay, yeah. Thank you, Jonathan. Thank you for answering the questions, and thanks for the talk.
Thanks a lot.
Before we move on to the third and the fourth talk, I want to do a quick shout out and a quick reminder that about the keynote session that's going to follow this paper session given by Joseph Shaw. Joseph Shaw is a wonderful speaker and an amazing photographer. And anybody interested in photography, beauty of nature, and physical effects of intricate things in optics of the outdoor and imaging in difficult conditions should watch this talk. I highly recommend staying tuned to the session and watching this keynote session after this talk. And he has also promised to give some photography tips, so that's something you can take away from it. So we're going to learn a lot from his talk, insights, and that is going to be also useful for this community. So this is just a quick announcement and a reminder that please stay tuned after this session to attend keynote talk by Joseph Shaw. With that, we can move on to our next and the third paper in this session. The third paper is also a physics optics abstract talk as the previous one. And the title of the talk is Polarization Entanglement-Enabled Quantum Holography by Hugo, Bienvenu, Ashley, and Daniel. The presentation is going to be given by Hugo. Let's watch the video of the talk.
Good morning, everyone. My name is Hugo de Fienne. I am a lecturer at the University of Glasgow, and today I'm going to talk about our work entitled Polarization Entanglement-Enabled Quantum Holography. To start this presentation, I would like to give a brief introduction about holography. Holography is an optical technique in which an intensity pattern is produced by diffracting coherent light onto a complex object. The information of this intensity pattern that we call an hologram is then used in order to obtain some information about the three-dimensional structure of the object. In practice, holographic imaging is often implemented using an holographic interferometry setup in which the diffracted light is superimposed onto a reference beam in order to produce the hologram at the output by interference. Holographic imaging is used in many fields of physics and imaging, and it's particularly useful in biological imaging, where it can be used to retrieve a three-dimensional structure of very small and transparent objects, such as neurons or cells. But one ingredient that is really essential in any holographic imaging approach is the fact that the light that is used must be coherent. Indeed, to achieve holography, we need to be able to produce stationary interference pattern. And to produce stationary interference pattern, we must use a type of light, a coherent type of light. In our work, I will show you that we can actually achieve holography without coherence, but using entanglement instead, in short to do that, we're going to essentially replace the classical source of light that I was showing you in this setup by a source of entangled photon pairs. So to be a bit more specific about this part, let me describe the source of photon pairs that we're going to use in our work. In our work, we're going to use a source of hyper-entangled photon pair, which means that the photons are entangled both in space and polarization. To produce these photon pairs, we simply illuminate two nonlinear crystals, so a pair of nonlinear crystals, by a blue pump laser polarized at 45 degrees. And the photons are produced by spontaneous parametric tone conversion where one blue photon becomes two red photons. These two red photons are produced at the outputs, and they are entangled both in space and polarization, which in practice means that we can measure correlation between both their spatial degrees of freedom, but also between their polarization degrees of freedom. To be a bit more formal, the state that we observe at the output has this form. In our holographic imaging setup, we're going to divide the system into two parts. On the left side of the beam, I'm going to have, which we're going to call the object arm, we're going to have a camera that we call the camera object. And on the right side of the beam, we're going to have another camera that we call the camera reference. If we use this camera as conventional camera and take intensity image at the output by accumulating photon, we observe that the intensity at the output is homogeneous on both sides. It's a half disk, but inside it's homogeneous. So in this case, we observe that measuring the intensity at the output do not give us any information about the collective behavior of photon pairs. And in fact, we could replace the source of photon pairs by any classical source that is incoherent, and we could observe exactly the same intensity at the output. In fact, the light that we are producing is also completely unpolarized, because when we put polarizers between the camera and the crystal and rotate the polarizer, we do not observe any change in the intensity at the output. So in fact, by measuring only intensity at the output, we are not doing something better than just building a simple imaging system with an incoherent and unpolarized source of light. To really exploit the fact that we are using photon pairs, and in particular exploit their entanglement properties, we need to perform coincidence measurement between the pixel of the sensor at the output. And to do that, we use a very specific type of camera, a single photon sensitive camera, that in this case is an EMCCD camera. An EMCCD camera enables to measure a four-dimensional coincidence matrix, so measure coincidence between all the pairs of pixels of the sensor and measure the joint probability distribution of photon pairs at the output. To visualize this four-dimensional matrix, we could, for example, project some conditional images. For example, let's consider a pixel A onto the camera object and measure the probability of detecting the second photon on the other camera when the first photon was measured at position A. We observe on this what we call a conditional image that the probability of detecting the second photon is maximum exactly at the symmetric position relative to the pixel where the first photon was detected on the object camera. We can also take another point, for example, and we observe the same phenomenon, that the second photon is always measured at a symmetric position relative to the position where the first photon was detected on the first camera. This anti-correlation behavior of photon pairs at the output is a signature of the momentum conservation happening during the SPDC process. In our work, we won't actually use all these conditional images one by one, but we are only going to form an image that we're going to call the coincidence image by mapping only the values of the coincidence between symmetric pairs of pixels of the two sensors. This image that, again, for clarity, we're going to call the coincidence image, is essentially an image that is formed from the coincidence measured between all symmetric pairs of pixels of the sensors. When there is no object in the setup, this coincidence image has exactly the same shape as the intensity on the reference arm. But now let's introduce a phase object in our system, and in this case, it's a birefringent phase object. When we introduce this object, we observe no change in the intensity. Of course, light is completely unpolarized and incoherent, so we do not expect any change in the intensity. However, we do observe that the coincidence image is now modulated by the shape of the object that we just introduced on actually the other arm. So this, formally, what is happening is actually a phase term is introduced by the birefringent phase object on one of the two terms that is forming the quantum state at the output, enabling this two terms to interfere when we perform the measurement with the camera, and then to have an image that is proportional to the phase, which is essentially an hologram of the phase object. So we are able here to measure an hologram of the object by performing coincidence measurements with our camera. But to achieve holography, we need more than one hologram. And to do that, to get more hologram and retrieve entirely the phase, we're gonna insert a spatial light modulator onto the other beam, onto the other side of the setup. This spatial light modulator will be used to introduce a constant phase shift in the setup, a constant phase shift that formally will be introduced on the second part, on the second term of the quantum state at the output, which will enable to essentially measure multiple holograms all shifted one relative to each other at the output. And with different holograms, it's possible to combine them to reconstruct the complete phase without ambiguity of the object, of the birefringent phase object that is positioned in our system. So this here describes exactly the protocol that we use to achieve holography with our system. What is important to note here is that entanglement is essential in this system to operate, because without entanglement, it's possible to demonstrate that if we remove entanglement by generating a source of photon pairs that is correlated in space and in polarization, but not entangled anymore in polarization, we still do not observe anything in intensity, but we lose any information in the coincidence image and we cannot retrieve the phase at the output. So entanglement, polarization entanglement in our system is essential for our system to work. Here we have demonstrated that it's possible, thanks to entanglement, thanks to polarization entanglement between the photon pair, to achieve holographic imaging, even if the light is completely incoherent at the first order and completely unpolarized. We have demonstrated our technique using, of course, artificially birefringent objects, using an SLM to program them, but also using biological samples, such as a bird feather that is a bit birefringent on certain part of it. And we also demonstrated with another object that's a Scotch tape that is birefringent. And also recently, we extended our approach into non-birefringent object by modifying the setup. So the question you would like to ask before the end of this talk is probably the fact, okay, yes, we demonstrated that we can do holography without using classical coherence. So without classical coherence, by using entanglement instead. And the question you would like to ask is what this could be useful for. Why do we want to do that? Why we want to do that? So just to finish this presentation, I would like to mention the different advantages that we have identified by using this quantum holography approach in comparison with classical holography. Our quantum holography technique has some advantages. The first advantage is the fact that quantum holography is robust against dynamic phase disorder. So if you have two random phase disorder on each of the two arms here that are rotating, completely random, you can still perform holography, and this robustness is connected to the notion of decoherence-free subspace that is known in quantum information processing. Another advantage of our approach is robustness against the presence of stray light. So if you have stray light falling on your sensor that is dynamic, you can still perform holography and retrieve the phase at the output. This robustness is linked to the notion of quantum illumination. And finally, we also have a better resolution compared to classical coherent holographic system. That is an effect that has been demonstrated in the past with raster scanning approach that we essentially extended here in full field in our holographic technique. What I would like to remember from this presentation is the fact that we have achieved holographic imaging using entanglement instead of classical coherence. Its application range is for birefringent object, but we also recently extended it to non-birefringent objects. It has some advantages, including the robustness against phase disorder, against noise and stray light, and also a better resolution compared to classical holography system. This robustness and advantages are linked to three specific notions in the quantum information processing field. In terms of perspective, of course, we want to go faster. So far, all the images that I've shown you have been taken using hours of acquisition, tens of hours of acquisition. By using faster camera, we can probably reduce this time to smaller, to minutes, for example. And we also, another perspective that is interesting is this notion of quantum illumination that could be used to implement both classical and quantum holography simultaneously. And finally, with that, I would like to thank you thank all the people who have been involved in this work, including Daniele Faccio, Ashley Lyons, Bienvenue Nagano, and I would like to thank you, all of you, for your attention.
Awesome. Thanks for the great talk. Here's the first question for Hugo. Are quantum entangled-based systems photon limited and thereby needing really long acquisition hours? Are there ways to overcome this limitation?
Yes, thanks for this question. So as you have noticed, I don't know if I mentioned it during the presentation, but the experiment we do effectively takes around 15 hours to 20 hours to get at least the 4 images in this case of coincidence images. So there are some way of going faster. In this case, it's not actually limited by the power of the source. So source of photon pairs have a very low power. It's typically around 1 picowatt, but it's not really the limit here because we have cameras that are very, very sensitive to single photon. In this case, it's CMCCD camera. It's mostly limited by the speed of the frame rate of the camera that we are using. So this CMCCD camera essentially can only go at a very low frame rate because they have this strong amplification process where the pixels have to go in series, and that strongly limit the frame rate. To overcome this problem of frame rate, we can use camera that just go faster, and SPAD arrays are typically the type of camera that can go up to 3 kilo frames per second using very, very small exposure time. And we have actually demonstrated that you can do similar experiments, at least counting photon pairs using SPAD camera in about 2-3 minutes, albeit that you have much lower resolution because the current available SPAD camera do not have yet a very good spatial resolution.
Yeah, that's true. Okay, thank you for the answer. Some question from the chat. Can you explain how do you image non-birefringent phase objects?
So to image non-birefringent phase objects, we have to modify the setup. So it's not the setup that is shown in the presentation. We have actually we get inspired from what is done in differential interference contrast microscopy, which essentially by using 2 birefringent plates, you can effectively transform a phase object, a non-birefringent phase object into a birefringent phase object. So it's not exactly purely like full phase microscopy, but if you do it in a simple way, it's a phase gradient microscopy. So you only see the edges and the variation in the phase of your non-birefringent object.
Okay. Okay, thank you. And one last question, and due to time, try to answer quickly, but here's a question. Are there situations in which coherent illumination is more beneficial than entangled photon pairs? Or do you see quantum holography eventually replacing coherent holography?
So in the current, so it's interesting. It's an interesting question because in this configuration here, so if you want to do, you cannot replace entanglement in this and by classical correlation in this experiment to perform this holographic experiment. You really need entanglement. However, it's true that classical holography is a common process that is done in many works, and currently this process with entanglement has some advantages. For example, the resolution, the robustness against some disorder and some classical and some stray light coming on the sensor. So it has some advantages, but considering the fact that it has also a strong drawback, that is the time of acquisition at the current stage before the development of new sensor that goes faster, it's probably at the moment better to use a classical holographic system than quantum holography. But it has a lot of promises for the future. I don't see what the future is going to be, but I believe it's going to be probably something hybrid between quantum and classical in the same time, depending of what type of sensitivity or a balance between the speed or the sensitivity of what you want to do in your experiment in the future.
Okay, thank you. Yeah, definitely looking forward to the future where this is also incorporated. There are a few more questions in the chat, but in interest of time, I'm going to move to this next paper. Do answer those questions directly in the chat. Thank you, Hugo. Okay, with that, we're going to move on to the 4th and the last paper in the session. Again, a reminder, after this paper session, there's going to be a keynote talk by Joseph Shaw. Please continue to stay tuned to the live stream. And the fourth and the last paper of the session is an ICCP paper. It's titled ReWave, Reference Wave Design for Wavefront Sensing. And the authors are Vayu, Matthew, Annette, and Ashwin. The presentation is going to be given by Vayu. Let's watch the video for the presentation.
We present ReWave, an adaptive imaging technique for wavefront sensing. It can recover a wavefront analytically and have applications including refocusing, correcting artifacts of optical components, as well as image behind a diffuser. The goal of a wavefront sensor is to measure the amplitude and phase of an optical wavefront. Consider a spherical wavefront denoted by U. Conventional sensors measure light intensity, that is, absolute value U squared, which in this case results in a uniform image. However, what is not captured is the phase of the light, the angle of U, an important optical attribute that is related to the distance light traveled. Wavefront sensors capture both the amplitude and the phase of an optical wavefront. For example, one such device is known as point diffraction interferometer. The idea is to take an incident wavefront as input and split the wavefront into two copies using a beam splitter. One copy of the wave refracts off a mirror, resulting in a wave that retains its original state, so the sensor receives our original field U. The second copy refracts off a small pinhole, which turns the wavefront into a planar reference wave R. These two wavefronts interfere at the sensor, which measures the sum of intensity of U, R, plus the real part of UR conjugate. If we can also change the phase of the light at the pinhole, we can get phase-shifted versions of the plane reference wave R. It is easy to show that with this information, we can isolate UR conjugate with three images under different phase shifts. Moreover, R is none, as it is a simple plane wave. Therefore, we can isolate the complex field U and recover our missing phase. This provides a very elegant solution, instead of the fact that since we place a pinhole, most of the energy in the reference wave is blocked, and the resulting reference wave is very dim, making this approach very sensitive to noise. Beyond the fact that we have blocked most light, the fixed position of the pinhole may be in a position where the incident field happens to have no energy. Our goal in this work is to open more than a single pinhole to collect more light. Moreover, we want to select the position of the holes adaptively such that they are placed at points where the energy of the incident wave is high. We do this by a two-step rearrangement in a setup. First, we don't really need to use two arms of the beam splitter, but we can make the two waves interfere at a single arm. For that, we replace the block part of the pinhole arm with a mirror. The pinhole itself also reflects light, but with a different phase. We can think of it as having a flat mirror area reflect the field U minus R, and the phase modulated pinhole reflect R with a modified phase. Thus, our sensor measures the interference pattern between U minus R and R after phase adjustment. This adjustment does not change the math that much, and as long as R is none, we can extract the incident field U. To implement this interferometer, all we need is the ability to change the phase at different points on the reflector plane, for which we use a phase-only spatial light modulator. So far, we have implemented the standard point diffraction interferometer using a spatial light modulator rather than an actual pinhole. By itself, this does not give us much, but I would like to remind you that our goal is to open more than a single pinhole and select position of these pinholes adaptively to be at positions where the incident field has high energy. For that, we use the second arm of the beam splitter, which is now empty, and place there a sensor. As the sensor measures the energy of the incident field, we can adapt the position of our pinholes to the spread of the energy on the plane. We can also open more pinholes to further increase the light throughput. However, recall that the main thing which allows us to recover U so elegantly in the point diffraction interferometry setup is the fact that the reference field R is none. When we open more pinholes, the reference wave becomes non-planar and its shape is unknown. Recovering it becomes a non-trivial wavefront sensing problem of its own. Our main contribution is in selecting the arrangement of holes in the reference wave in a special way that will still allow us to estimate it analytically. To recover the reference wave, we know that by multiplying the image measured by the sensor at the top with the mask of pinhole position, we can get the intensity of the reference wave in the Fourier plane. And with sound processing, we can also eliminate U from the image at the lower sensor and isolate the intensity of the reference wave R. Now we have the amplitude of the reference wave in two planes. And according to the Wiener-Khinchin theorem, we can perform inverse Fourier transform on one image to get autocorrelation. Autocorrelation is very useful to reconstruct a sparse wave. Suppose our reference wave is composed of two pinholes, so it is a sparse wave with only two entries. Its autocorrelation values will correspond to multiplications between the two entries. We can arrange these entries in a matrix and reconstruct the wave by using SVD to find the rank 1 component. We can extend this idea for a sparse signal with n entries, but we need to select these positions in a special way that we characterize in the paper as a collision-free layout. For collision-free pinhole arrangement, we can still solve for the wavefront analytically. For more details, please refer to our paper. To evaluate our approach, we compare it against several previous strategies. We attempt to recover wavefront from 32 noisy measurements. The tested wavefront had a uniform amplitude and a phase shown on the slide. First, we consider the basic Churchburg-Saxton algorithm, which measures the amplitude of the wave in primary and Fourier planes and solve an alternate optimization problem to recover the wave. This method itself only needs two images, but we can capture the same image multiple times to reduce noise. Typically, for complex wave, this algorithm does not converge to a correct result. The second method is multi-plane propagation that measures the propagated waves in multiple planes and uses an algorithm similar to Churchburg-Saxton to solve for the phase. Here, we capture results from 32 planes. While it does reconstruct some parts of the wave, it did not converge to a correct result. The third method we considered is a recent successful phase estimation strategy named WISH. It modulates wave with several random phase patterns, which is 32 masks here, and measures the amplitude of the waves which propagated through these masks. It usually reconstructs a good result, but may still leave some artifacts. We also compare with point diffraction interferometry. It only requires 3 images to get a wave, but we can capture more images to reduce the noise. While it can reconstruct a correct wavefront, its reconstruction tends to be noisy since it has a dim reference wave. In comparison, our method with a brighter reference wave can reconstruct a clear and accurate wavefront. Similar to point diffraction interferometry, we need only 3 images plus 1 in Fourier plane to reconstruct the wave, but we can choose different combinations of pinholes to get more waves and average their results. We performed a quantitative comparison attempting to recover multiple phase patterns under 2 noise conditions. Under noise-free conditions equivalent to an SNR of 60 dB as shown on the left, the point diffraction interferometry, which is marked here as a purple curve, provided the best result. In noisier 20 dB condition on the right, the WISH approach plotted by a yellow curve outperformed. Our method outperforms all approaches in both cases. We have built a lab prototype to optically implement our ReWave method. And we also implement some of the competing alternatives in hardware. In this comparison, we attempt to reconstruct a quadratic wave. We show reconstructions when we allow each of the algorithms to capture 8 or 32 shots of the images, with possibly different masks. Both Churchburg-Saxton and multiplane propagation failed to reconstruct this wave. Point diffraction interferometry succeeded, but led it into a noisier reconstruction. And our method provided a crisp result, which is not implemented here because it requires a different setup. Now we demonstrate applications of ReWave. Here we capture the phase of the wavefront propagating through a microscope slide. Once the amplitude and the phase are known, it is possible to refocus the image of this slide by propagating the wave to planes at different depths. For example, here we visualize the amplitude of the wavefront at two different depths, each showing a different cell in focus. Here is another example of a B-lag under a microscope objective lens. Once again, it is possible to refocus the image in post-processing. At one depth plane, we can see the dust particles on top of this slide. At another depth plane, we can see the details of the B-slag. ReWave can also measure a clear phase pattern of a Fresnel lens. Fresnel lens, as shown in the bottom left, is a phase mask with quadrilateral pattern. When we zoom in, we can clearly observe the quadrilateral phase pattern across this phase image of the Fresnel lens. We can use this information to form high-resolution images of a target with nothing but a cheap Fresnel lens. While your Fresnel lens attempts to focus the light with a small f number, it is a very low-quality lens, and the image it forms is subject to many aberrations as we demonstrate here. However, with our ReWave setup, we can measure the phase of the Fresnel lens precisely. We can then use this phase to correct this wavefront and recover a clear image of the resolution chart. Similarly, we can measure the phase of a diffuser. If we attempt to image a resolution chart beyond this diffuser, we get a scrambled image due to the diffuser. However, after measuring the diffuser, we can correct the aberration it induces and recover a clear image of the chart behind it. To summarize, we have introduced ReWave, an approach to design a reference wave which is extracted from the object itself. Unlike classical point diffraction interferometry, it generates a bright reference wave. Assuming the reference wave is selected to satisfy collision-free conditions, we can solve for it analytically. We have demonstrated the robustness of our approach using both synthetic and hardware comparisons. Thanks for your attention, and please refer to the papers for more details.
Thank you, Wei, for the presentation. Here is a question. So collision avoidance seems to be a crucial part in your method to keep the solution elegant. Can you very quickly talk about how are the points chosen to avoid collision?
Okay, it's a good question. So in short, you want to choose the points that any two points between them has a unique displacement. So think about the autocorrelation. The autocorrelation is the image itself multiplied by a shift copy. And so if any two points has a unique displacement, then when you shift one image and multiply with other, then autocorrelation will correspond to just multiplication between 2 points. And it's a key to reconstruct the wave from the autocorrelation.
And in your technique, is this the most computational complex aspect, or this is very little computational complexity?
So are you asking about, is this the most difficult part to reconstruct during my reconstruction? In sense
Yeah,
of the
does this take the most time?
And it's not, it stays the most time in computation, but it is still very fast. Basically, you can do it in real time.
Okay, thank you. There's some more questions in the chat. In interest of time, I'm going to end the session. You can go to the chat and also answer the questions. Thank you, Wei. All right, so thank you all for attending this session. This would be the end of this paper session, but the stream will continue to have the next keynote talk, which is going to be an exciting talk given by Joseph Shaw. Please stay tuned to attend the keynote session. Thank you.
Hello, ICCP. Thank you very much, everybody is joining. Yesterday we had a very nice day in person in Israel, and it's good to be online as well with you. We are really privileged to have very soon the talk by Joey Shaw. So I want to say, before I'm talking about Joey Shaw, just to tell you about the community that he's in. So there's a community called the Light and Color in Nature community. You must have seen some of these books about light and color in nature. And there's this community, and they meet every few years. And I was in one of these meetings, and they all walk around with an SLR. So that's how they live. You know, you sometimes you walk in your life and you see something and you say, I wish I had my camera. So they never say that. They always have their camera with them. So whenever they see something interesting, they take an image. And whenever they see something that you don't think is interesting, for them, it's interesting. And they see the beauty of nature everywhere. And Joey Shaw is a prime example for this. So he is taking very unusual images from very interesting angles of things that are regular and irregular, and then he shows something really interesting going on there. His photographs are really beautiful. They appear on all sorts of covers and I think calendars. He has a book, Optics in the Air, that just came out a couple of years ago, where for many flights that he took photographs from the windows of from the window of the airplane, and sees all sorts of amazing effects. Joey Shaw is a professor at Montana State University, a distinguished professor there. And as I said, he's a dedicated photographer, a physicist, and author of books. He won the Presidential Early Career Award for Scientists and Engineers. He's a fellow of OSA and the SPAE. But I would also mention a few awards that you may have not heard of very often in our community. So the Stokes Award for Optical Polarization and the Vaisala Award from the World Meteorological Organization. So this is going to be a very fun talk about photography, about optics, about nature. Thank you very much, Joe.
Thank you, Yoav. Let me go to sharing here. It's really my pleasure to be here with you today, and I wish I was there in person in Haifa with everyone. Okay, now I'm ready. So we will talk about photographic exploration of optics in nature and the science that goes with it. As Yoav said, I'm at Montana State University in the United States, and it's really my pleasure to be here today. This is a little bit of a map to show you where I am right now, speaking to you. It's morning time in Montana in the northwest United States, and I am just north of Yellowstone Park. Yellowstone Park, if you've ever been there, is right here, and just kind of my backyard. So here's what it looks like around here. My objectives today are to share some photographs that are of things that I think are interesting and beautiful, and to summarize some of the scientific research that's motivated by some of these photos. And maybe I can inspire some of you scientist photographers to also carry a camera and observe and study nature. So when I was young, when I was a teenager, the only two things that I was really interested in were, well, other than the usual girls and things like that, were music and photography. And so when people asked me what I wanted to do when I grew up, I didn't really have an answer. You know, well, I want to be a rock star or I want to be a photographer. And so I sort of became a photographer, but a scientist photographer. When I was 20 years old, I was in southern Japan, and I took this picture from a train. And I did not really understand it, but I always wanted to understand it. And I think we'll come back to this in just a moment. This is a glitter pattern of the sun setting here, reflecting from the water. About 13 years later, I found myself as a PhD student in optics on this strange looking inverted ship. It's called FLIP. It's called the Floating Instrument Platform. And that acronym is FLIP because it is a ship that floats horizontally and then flips vertically. And this instrument right here is my instrument that I built for my PhD dissertation. And it was called a laser glint meter. There were actually two instruments. There was a laser glint meter and a laser glint imager. And the data that I'm showing you here on the right is an example of a slope probability density function from the laser glint meter. And so what this shows you is I scan a laser beam across the ocean surface and create very much this kind of pattern. I create a glint pattern, but instead of using the sun, I use the laser. And that's good because you can see it's a cloudy day. And this allows us to get measurements despite whatever weather there is, and also at night. And what this is doing is measuring the slope distribution of the water. And it's kind of Gaussian, but not exactly. And the differences are very important. So we published a couple papers about that, and including the fractal nature of the glints from the imager. And one of the most important scientific results that came out of that is that there's this famous relationship called the Cox-Monk relationship that relates the width of that curve, or the mean square slope. So the surface roughness, the Cox-Monk relationship relates the surface roughness to wind speed. And you can therefore measure this by looking at the roughness of the surface from space with a radar and measure the wind speed over the ocean. But what we found is that the Cox and Monk relationship needs a correction based on the difference between the temperatures of the air and the water. And so you can see here, when the air is less than the water, you get into this negative stability condition where the roughness can double from what the Cox-Monk relationship predicts. So that was an interesting piece of science that came out of glitter patterns. So let me explain to you a little bit about how glitter patterns are formed. I will assume the sun is a source, but we could have the moon or the sun or a street light or whatever. And if we have a flat surface, we have a specular or mirror-like reflection that brings the reflection of the sun to your eye. But if you have a ray that comes over to this point, the specular reflection misses your eye. And similarly over here, it misses your eye. But if you tilt those surfaces to just the right angle, then those can bring those reflections to your eye. And so because of that, with a flat surface, you expect only a localized reflection. But for a rough surface, you get a streaked out pattern that we call a glitter pattern. And here's an example picture that I took actually when I was standing next to Yoav. And this is at the Sea of Galilee. And I noticed that where this protected water is right here, the sun is giving us it's very smooth water, so we get a very specular reflection. But over here, the waves are coming in and there's a rough water surface, so we get many glitter points. And this illustrates the difference between the smooth water and the rough water, all in the same picture. And in fact, here's a picture of Yoav and me standing next to here some years ago. If you look closely at a glitter pattern, you can tell that there are individual reflections. You can see that in this case, it's a very smooth water surface with just a little bit of wave action. And you can see these bright glints. occurring at each point where the angle is just right to produce a specular reflection. And then, of course, when the water roughness increases, usually because of wind creating capillary waves on the water, you can get this nice streaked out pattern. There's a lot that I could say about the geometry, the ratio of the length to the width, but it's a little bit too much and I don't have time for it. But it's a function of the altitude of the source, the altitude of the observer, and the roughness of the of the surface. But even here, when you look close at the close point, you can see the individual reflections that make up this pattern. And here's a different view on a lake where you can see very clearly that there are individual glints that make up the glitter pattern. And so here's a glitter pattern that I photographed. I believe this is on the Mediterranean, actually, coming to Israel. And you can see that the very bright region is the specular region, where we get the specular reflection if it were a flat, smooth surface. But then you get this spread out pattern that occurs at other angles. So it turns out you can see the same kind of thing with ice crystals in the air. And so when there are ice crystals in the air, they are almost always these some form of hexagon shape. So we can have flat plate crystals, we can have long pencil crystals or column crystals, but they all have hexagonal cross sections. And so looking at the ray paths through a hexagonal crystal can predict many types of halos. But for now, let's ignore the refraction and let's just think about reflection. If the sunlight comes down and reflects from the top of the crystal, it makes a very bright glint. And so we can form what's called a light pillar or a sun pillar by reflections from the ice crystals. And it's the same thing as what we have with a glitter pattern on water. We have here a reflection from a flat crystal. And these crystals, by the way, tend to fall or float in the air with their flat surfaces down like this. In other words, they tend to orient themselves naturally from aerodynamic forces. They orient themselves so that they are horizontal or nearly so. And so same story here, right? That if there's another crystal down below here, the specular reflection misses your eye. But if you tilt it just a little bit, you can bring that reflection to your eye. And similarly up here. And so now with this collection of tilted crystals, we get glints at 3 different points, or in reality, many different points. And that gives rise to this kind of effect. This is called a sun pillar or a light pillar. And the sun is actually below the horizon, and it's reflecting off of ice crystals in these clouds. And so we can see this vertical pattern that looks just like a glitter pattern on the ocean, except for now it's vertical. And here's an example of that from headlights of a car driving in a snowstorm. And in this case, the snow crystals are large and flat and falling like these hexagonal crystals, and they form a vertical pillar. If the crystals are not moving much, so if the air is very calm without much turbulence, you can just get here's the sun, and here's a reflection of the sun at the specular point below the horizon, so that the angle between the horizon and the sun is equal to the angle between the horizon and the sub-sun, or the specular reflection. So we call this a sub-sun, and it's very bright. It's not large, but it's very, very bright. It can be very entertaining to look at from an airplane window. And these are just reflections off of the tops of crystals in a very still atmosphere. And I'll show you a couple Oh, I just put this picture in to remind you that that's just like this. That's like the specular reflection off of the calm water. So here I'm going to show you a couple examples of subsuns. You can see that this subsun is starting to be stretched out in the vertical direction a little bit. And that's because the crystals are starting to wobble or, you know, rock back and forth. And they have some tilt distribution. And the larger the tilt distribution, the longer the subsun becomes. And we call that a subsun pillar. This is actually a picture taken on an airplane leaving my hometown, and this river is coming out of Yellowstone Park. So here we have an example of a subsun that has been stretched vertically into a full pillar. So we have a full subsun pillar, and that's because of the ice crystals at all different angles in those clouds. If you manage to get up close to one of those subsun pillars, like when the airplane is landing, you can see the subsun is up here, but below it, you can make out all the individual crystal reflections. And then if you ever look at these subsuns, you should keep your eye open and pay attention. If you ever see this, you should definitely take a picture, because this is a very rare halo called Bottlinger's ring, and nobody really understands completely how it's formed, but it's a oval. This is just a normal subsun, but then here's an oval halo around it. And I remember when I saw this, the airplane was landing, and this is back in the days when the flight attendants used to make you put away your cameras and everything because the electronics are going to damage the airplane. And the flight attendant was very angry at me because I was not putting away my camera, but I knew this was a very famous photograph that I was getting, so I was not going to put my camera away. But luckily I did not go to jail over it, but I did publish a paper about it. So I don't know, I think I've only seen maybe 4 people who have published pictures of Bottlinger's ring. So it's very rare. So keep your eye open for that. When we ran some simulations, my colleague Les Cowley, who is in this light and color group that Yoav mentioned, and he also runs the best website in the world about optics and nature. Just look up Atmospheric Optics webpage and you'll find it. And he did some simulations for me, and the only way that you can reproduce Bottlinger's rings that we've discovered so far is by assuming a crystal that has this kind of shape, and the different features come from these different ray paths in these tapered hexagonal crystals. The problem is some of the crystal people tell us that this is not a very likely crystal. Maybe that's why it's so rare though. So we don't know if this is actually how it's formed, but it's one possibility. Okay, so if we go to a more conventional hexagonal crystal, and now let's go ahead and consider what happens with refraction in the crystal. If the sunlight comes in to these faces that are 60 degrees apart, then they come out making these minimum deviation ray paths 22 degrees deviated from the original direction. And that creates the famous sundog that everybody knows and loves. These little splashes of color are called parhelia, but the parhelia are more commonly known as sundogs. And so here's one on the right side of the sun, here's one on the left side. Sometimes you only see one, and sometimes you see both. This is caused by those refractions that I just showed you. But in order to have just a splash of light in one localized spot, we have to have very horizontally oriented crystals, very much like the flat water surface. And so as soon as we roughen the water surface, or in this case, as soon as we start making the crystals rotate into different angles, you can get a sundog at all angles, but they're always at 22 degrees, and so it makes a circle of radius 22 degrees. And so you can see that it's a very large circle. It's not as large as a rainbow, but it's a still very large circle in the sky. And it contains some color. That's something I should have pointed out. In fact, maybe I'll go back and just point it out, that when we have these subsuns and reflection phenomena, there's no color because we're just reflecting white light, and the reflection has no wavelength dependence, or very, very little wavelength dependence. But the refraction actually has wavelength dependence because the refractive index depends on wavelength. So because of dispersion in the ice, we do get some spreading of colors, but most halos aren't really strongly colored, but you do see kind of a red edge, and then it fades to blue on the outside. And the purity of the color depends primarily on the how clean the ice crystals are. So you might think, well, I'm in Israel, I can't see ice crystals, but that's not true, because here's an ice crystal halo that I photographed in Arizona, which is nice and hot almost all the time. And the reason that you can see a halo in a place like Arizona in the desert is because even if it's like 30 or 40 degrees C at the ground, if these clouds are up at 10 kilometers altitude, you would expect the temperature there to be about -40 degrees C. And that's certainly cold enough that we expect ice crystals. And so we can get ice crystal halos surrounding a palm tree. Now, I live where there are ice crystals in the air in the wintertime. And so one day looking out my office window, I saw this, and this is a subsun. So this is a subsun pillar, and it's actually catching just the edge of the halo. So the sun angle was just right to make the subsun pillar occur right at the edge of the halo. So you get this splash of color at the top of the white pillar. Another combination of effects is shown in this photo, where we have the sun, the subsun with a little bit of vertical stretching because of different angles. And then if you look off here to the right of the sun, we have a sundog. And the sundog is vertically stretched just a little bit, just like this is vertically stretched, for the same reasons. The crystals are oscillating in the air. You can, of course, do simulations on a computer. And in fact, if you go to Les Cowley's website, you can download ray trace code. But this is just showing you the different shapes of crystals that we typically see, and some of the different halo arcs that you can create with those different ray paths. I'm going to show you maybe one more example, and it will include this arc called the upper tangent arc. And the shape of that arc depends on the altitude of the sun. And so here we have the sun setting behind the mountains on a cold winter day, and it's creating a sun pillar by reflection from the crystals. The reason these reflections are colored is because the sunlight that's hitting the crystals is colored because of the long ray path from the setting sun. But then up top here we have this V, which was created. This is the upper tangent arc. So this is 22 degrees. The corner of this V is at the 22-degree halo. So if we had a halo, it would be down here. But in this case, there's no halo, which means we were not getting the right kind of ray paths through the crystals. And I think I have, yeah, here we go. This is the ray paths that we get to create the upper tangent arc, is this blue ray coming in, very, very similar to the ray paths for a 22-degree halo, but just through the opposite faces on a horizontally oriented, almost horizontally oriented column crystal. So the column crystal then creates this shape instead of the flat plate crystals that create the halo. Okay, let's move to rainbows for a minute. If we assume for the moment that water droplets, that raindrops are spherical, they're not, but let's pretend they are. They're, at least in one axis, they're almost spherical. We get refraction here. So because of dispersion, the blue bends more than the red, and all the other visible wavelengths are in between. At the back, most of the light goes through, but we get a reflection. We get another refraction as we leave the water and go into the air, and that creates the primary rainbow. And then the secondary rainbow comes about in a similar process with 2 reflections and 2 refractions. If you extrapolate backward, you see that you have to remember that when you're down here observing the rainbow, you don't see the angle of the rays, you see where the light appears to come from. So the red appears to come from here, and the blue appears to come from here. So the red should be on top and the blue on bottom. Whereas in the secondary bow, the blue should be on top and the red on the bottom. So the color order is reversed. And also, because you lose a lot of light at the back of the drop, and you have 1 reflection here and 2 times here, we expect the amount of light coming out to create the secondary rainbow to be much less. So the secondary bow should be much less bright. And we see that here. Here's the primary bow with red on top and blue and violet on the bottom. And if you look closely, especially over here against the dark clouds, you can see that the blue is on top and the red is on bottom for the secondary bow. This is in my backyard, and you can see the geometry. The sun is behind me, and here's my shadow. And the rainbow actually creates a circle, and that circle is centered on the anti-solar point. In other words, my shadow point. So that's the center of the rainbow. So if the sun is high in the sky, the rainbow will be low. If the sun is low on the horizon, then the rainbow rises high and becomes very beautiful like this. And you might notice that the sky is brighter inside of the primary bow and darker outside. And I'm going to discuss that right here. That's called Alexander's dark band, and it's a result of all the light clustering near a minimum deviation angle, which is shown here. As we get different rays coming into a sphere, we get a cluster of rays at this minimum deviation angle, shown in red. And all the other rays are coming sort of clustered above it. And if you extrapolate those backward, those would brighten up the sky below the rainbow. So that's all these rays right here are the rays that give us light down here. But there are no rays out here at the other angles, which is these angles. So these angles are dark because we took that light to create the rainbow. That's the way I like to think about it. And here you can see a close-up picture of the rainbow. Here's the primary, the secondary. The colors are reversed, dark in between, and the secondary is much darker than the primary. If you put a polarizer on your camera, I do a lot of polarization work, like Yoav was saying, and so I'm constantly looking at things with polarizers. And what you find if you do the theory is that rainbows are polarized tangential to the bow. So if you put your polarizer axis tangential to the bow, then you can actually enhance the rainbow compared to the background. And if you rotate it 90 degrees, you can get rid of the rainbow. So it's kind of like being a Scrooge, getting rid of the rainbow, but never fear, it's still there. You just got rid of it temporarily. You have to be careful of that. If you're looking for rainbows, you have to be careful if you're wearing polarized sunglasses. You have to either tilt your head or take your glasses off, because you might miss the rainbow otherwise. And if you go through the theory of the rainbow, at least geometric optics, you have a refraction here, a reflection, and a refraction here. And it turns out those two phenomena, the reflection and the refraction, if you think about the Fresnel reflection coefficient and the Fresnel transmission coefficients, they have opposite polarizations. The reflection favors, I guess, what we could call horizontal polarization, horizontal meaning in and out of the screen. And these ones favor the vertical polarization. And so because of that, there's a contest going on. There's some polarizing here, and polarizing here. And it turns out the dominant polarization wins out from the reflection, and we end up having a polarization that is horizontal at the top of the rainbow and vertical at the side of the rainbow. This is not a very good photograph, but I'm showing it to you because it's a time when I captured an interesting thing. Here's a very plain rainbow in visible light, and then I put a filter on my camera to block the visible light and transmit the infrared, the near infrared. And you can see the trees become very white looking because of the reflection, the high reflectance in the near infrared. But you can see both rainbows. And if I toggle back and forth, use this point as a reference. Here's the top of the tree, and you'll see the infrared rainbow moving compared to the visible rainbow. First of all, where should it be? If you think about it, well, here's blue on the inside, red on the outside, so infrared should come next, right? So the infrared rainbow should be outside of the red rainbow. And sure enough, it's out here. If I toggle back and forth, you can see the infrared rainbow jumping to where it should be. And so the only way to do this, of course, is with your camera on a tripod so that you can get the same orientation. So that's kind of fun to play with infrared photography a little bit. Sometimes when you look at rainbows, you see these extra rainbows. And I've had people ask me questions about, is this a third or a fourth order rainbow? And the answer is no. This is what's called supernumerary bands. These are interference bands. So far, we've only really talked about rainbows as a geometric optics phenomenon. But if we consider the wave optics picture, ray paths that take slightly different but nearly similar paths through the water drops can interfere and produce interference. But in order for that to be visible, the water drops have to be small, and they have to have very small drop size distribution. If we do a Mie scattering calculation, this is the brightness of the scattering on a log scale and scattering angle on a horizontal scale, linear scale, from zero. Zero scattering angle means that the observer is looking at the sun. 180 degrees scattering angle means that you're looking at light that is scattered back toward the sun. So you're looking at your shadow. So this is your shadow, this is the sun, and 40 or so degrees away from your shadow is this thing called the primary rainbow. Here's the secondary rainbow. And we can see that the Mie scattering calculation predicts these oscillations. Those are not the colors, because this is all at one wavelength. Those bands are the supernumeraries. Those are the interference bands. We see Alexander's dark band here in between the two rainbows, and we see the secondary. But we also see that there's two things that are interesting going on. There's another bright spot here around the shadow, and another bright region here around the sun or the moon or the source. Those have names, and we're going to look at them briefly. This is the glory, and this is the corona. If we put much, so these were for 500 micron droplets. This is 10 micron droplets, like cloud droplets. So if we start looking at cloud droplets, you also see that there's a rainbow, but it's now called a cloud bow. It's similar to the rainbow, but it's broader and it's much more white. You don't see any hint of the whiteness here because I'm only showing you one wavelength. But if you do this for all colors, you find that the colors overlap. But now the glory is greatly enhanced by looking at the small droplets. So this is a backscatter phenomenon, and this is a forward scatter phenomenon, the corona. So here's an example of the cloud bow. You can see this is Mount Rainier near Seattle. And this is a cloud bow with almost all white, with just a hint of red color on the outside. Here's another cloud bow, and the interesting thing here is you can actually see the bow extending up above the cloud, which means there are cloud droplets up there. And you can see a hint of a supernumerary interference band right inside here, but really no color. And then finally, an example from Yellowstone Park. I like to go to Yellowstone Park and take pictures, especially at night. And so this is a hot pot. This is a thermal feature, and this hot water is putting off steam, and the steam is producing a cloud bow, but it's really a steam bow from the moon behind me. You can see I'm sitting here with my camera on a tripod. And putting them together then, here's the cloud bow, and here's a glory at the center of the cloud bow. This is a particularly colorful example of a glory, and that's 3 orders of scattering. You can see 1 order, 2, and 3. If you look at the Mie scattering plots with red, green, and blue, now you can see that, yeah, there's not much color in the cloud bow, but the glory does actually have some color. And you can see that if you zoom in, you can see that the blue and the green and the red have peaks that occur at different locations. So we should have a blue fringe with a red outside. And that's what we see with the glory. And so again, here's an example of a more conventional glory. If you get closer to the cloud, you can start seeing the glory with the airplane shadow. And there's an interesting game you can play, because the glory is a constant angle scattering phenomenon, but the airplane shadow is a geometric optics phenomenon. And so as you get closer to the cloud, the glory will stay the same size, but the airplane shadow will get larger. And so here's a sequence of pictures that I took. You can see it's the same cloud. You can see this little feature up here. It's the same cloud, we're just closer to it because we're landing. And you can start telling that at the center is my seat. You can tell what seat I was in. And we get a little bit closer and the airplane is bigger. And then right when we go into the cloud, we still see a glory, and it's surrounding my head, but my head is inside of the airplane. And there we go. Turn around now and look toward the sun, and you see this effect, the corona. And here I'm using the edge of a building to block the sun so that I can get a well-exposed picture of the colors. And those colors will form nominally spheres, circles around the light source. This corona is not caused by this street light. I'm just using the street light to block the sun so that I can see the colors. And if you look down here at the feature, you might realize what city in the world I'm at. This is in Paris, and this is a really beautiful corona around the sun. And sometimes mountain wave clouds have some of the best coronas. This picture was taken by my colleague Paul Niemann, who I worked with many years ago. Mountain wave clouds are created by the air being blown upward. The wind is blowing horizontally, and it encounters a mountain, and the air goes up and creates a cloud. And that cloud tends to have, these mountain wave clouds tend to have very, very white color. They have very small droplets and very uniform drop size distributions. And because of that, they can make some of the very most beautiful coronas. Paul and I were comparing our photographs one day, and we started doing some analysis, meteorological analysis. And we realized that about 2/3 of our photographs of mountain wave cloud coronas were at altitudes that we would expect the clouds to contain ice crystals. But the textbooks all told us that ice crystals cannot create coronas because the ice crystals are too large. Because you can think about this as diffraction around droplets. So you have to have a very small droplet to get a large enough ring to see it. And so how do we get ice crystals that small? It was a mystery. And we went and visited with a guy named Andy Heimsfeld, who's a well-known cloud physicist. And he laughed and he went in and got this picture and he gave us this photograph. These are conventional ice crystals. These are the ice crystals that they collected when they flew an airplane through a wave cloud. And you can see they're little quasi spheres, and they're very small. They're on the order of 10 microns, which is just about the size of the water droplets in these clouds. And so that's the explanation of the mystery. And so we had an explanation, but we still wanted to have direct proof. But we published a paper and said, this is what we think is happening. And several years later, after I moved to Montana, I was driving home one night and I looked out the window and I saw this beautiful corona around the moon. And I realized, oh my gosh, this is my opportunity to prove that this is ice, because I earlier in the day had been probing these clouds with my LiDAR. So we have a dual polarization LiDAR in the lab below this port. And the beam, when we open the port, the beam comes up into the sky. And so we're just probing the edge of this cloud. This is a wave cloud, a very thin wave cloud. You can see the constellation Orion here. So here's the wave cloud, and the moon is just in the opportune location. We have these beautiful rings. And over here, I have altitude profiles of temperature showing that it was about minus 70 degrees up at this altitude. That's the altitude where the cloud must be, because that's where the relative humidity is highest. And at that same altitude, my LiDAR measures a strong backscatter signal from the copolarization. And the important part is that we get a strong signal from the cross pole. That means that we're launching, let me say that better. We're transmitting a laser beam with one polarization, this one, and we're detecting signal in an orthogonal polarization. The only way to do that is by having ice crystals up there, and because liquid water will not generate copolarized backscatter or cross-polarized backscatter. So this cross-polarized signal is the first proof that wave clouds really do contain ice that is creating that corona. And so that was fun. That was a fun little paper to write. And then finally, I'll show you a corona that has a very interesting situation. At the cloud edge, we have very, very tiny droplets. And the size of the corona is inversely proportional to the size of the droplets because it's a diffraction phenomenon. And so you can see there are larger particles out here in the air and smaller droplets in the edge of the cloud. So we get two different size corona rings right next to each other. This was in New Mexico just a couple years ago. Okay, let's go back to polarization for just a minute. I'm watching the time and I know we're getting a little bit short, but we're still okay, I think. Oh, maybe we're not. I better get out. Okay, so I need to wrap up. My timer on my phone stopped, and I thought I had more time than I do. So, okay. This is a scattering plot that shows that we have degree of linear polarization of 1 at 90 degrees for pure Rayleigh scattering. And that says that the sky can be polarized 90 degrees from the sun. We built an imager that does all sky imaging of the sky with polarization sensitivity. We do it with a fisheye lens, some liquid crystal variable retarders so that we can electronically vary the polarization, a fixed polarizer, and then a refocusing lens onto a camera. And we can get these circular images. These are circles of the sky with the zenith at the top and the horizon around the edge. This thing right here is the occulter that blocks the sun. So the sun is here, here, and here. And there's always this band of high polarization oriented 90 degrees from the sun. So it moves with the sun. throughout the day. And down here is the angle of polarization. I'm not going to take the time to explain that in detail, but the angle of polarization can be really fun actually to explore. What I want to do is explain that Rayleigh scattering predicts the basic polarization, but you have to do multiple scattering to explain what we actually observe, which is neutral points. So the sun is over here, and just above the sun, there's a region of zero polarization called the Babinett point. So this is this image plotted on a scale with a maximum of 0.04. So 4% polarization. And we do that so that we can accentuate these neutral point regions. There's one here, and there's one across the sky called the Arago neutral point. And you can also see them as discontinuities in the angle of polarization plot. I introduced that because I want to close with a brief story about a solar eclipse. In 1973, this guy, who happens to be my father, Glenn Shaw, went to Africa, and he measured with a scanning polarimeter, he measured scans of the sky polarization. And you see the normal scan here before the eclipse with high polarization, 90 degrees from the sun. And then during totality, you see this nearly symmetrical scan centered on the zenith. So he published a very famous paper and said the sky polarization in totality is nominally symmetric around the zenith. And then in 2017, we realized, hey, we have a solar eclipse very near where we live. So we drove a couple hours down to Rexburg, Idaho, and we were at the observatory of Brigham Young University, Idaho. This is my father, this is me, and these are students working with me. And we used our all-sky polarization imager to record images like this. Here is totality. Here's the eclipsed sun. And you see that there's an orange band all the way around the horizon. If you've never seen a total solar eclipse, you must. It's an absolute life-changing experience. But what happens now is that you go very suddenly from having the source being the sun to now the source is the light from the horizon. And that's where the symmetry comes about. However, it's not as symmetric as you might think. And so this is a plot that shows these are all sky polarization images from the beginning of totality to the end of totality. And you can see the only time that we actually get what my father predicted, or almost what he predicted, is really at the very end. You get almost a complete circle. His theory predicted a donut. And you don't ever really get a donut. There's a bite out of the donut that gets smaller and smaller and smaller until totality is over. And we very briefly, I just want to explain that we captured the very first ever digital images that show the transition out of totality. There's this neutral point at the zenith, which is unique to totality. And out of totality, you have this Babinett point that we talked about earlier. And we captured some images showing that what happens is this neutral point shifts down to become the Babinett point. So it's kind of fun to see that transition. So I will conclude by saying I've shown you 5 examples of nature-inspired science with glitter patterns, halos, infrared rainbows, ice crystal coronas, and the polarization during a solar eclipse, which this background picture is from that eclipse during totality. And I would like to thank you for your attention, and I hope that this motivates you to let nature inspire you to do some science as well. And then finally, I'll just mention, Yoav told you that I had a book called Optics in the Air. You can buy it from SPIE or on Amazon. So there it is, and I'm happy to answer any questions.
Joe, I am amazed, of course, every time. I think people in the audience were really, they're really inspired by your talk. It's a beautiful talk, and there's some people who posted questions. I also have some questions. So Lars says, it's a beautiful talk. Many explanations are on the microscopic level, right? Where the light is spatially coherent. But are there atmospheric optics phenomena that can only be explained over longer, maybe mesospheric spatial ranges? So are there any phenomena that require an absence of spatial coherence?
That's an interesting question. I can't think of an example right now, which means as soon as we're done here, I'll think of one, but I can't think of one right now. But yeah, we're only, I guess I would just comment, we're only really assuming coherence when we do the interference fringes kind of thing. But yes, it is basically assuming spatial coherence because the scattering otherwise would wipe itself out. So I can't think of any good examples of where we can just totally relax that. Maybe sky colors. I mean, but even that is a microscopic explanation of scattering by the molecules.
Yeah.
But there's no features in there that come about from lack of spatial coherence or come about from coherence.
Yeah. And Ori Katz mentions that he often sees coronas around streetlights when he walks in the fog. And so that's basically it, right? That's the same thing that you're talking about. The coronas around, are the halos around streetlights, that's coronas.
Yeah, you can see those. And the other time, I wish I had the picture to show you right now, but one time I was in a hotel room in Japan and I noticed that the sun was reflecting off of a building across from my hotel, and that was acting as the source. And then it was coming through the window, and the window was foggy because I just took a shower. And that moisture on the window was also creating a corona. But the source in this case was a reflection off of the building. And so, yeah, it's the same thing.
So basically coronas are all around us. We see them very often. We just didn't know that that's what they are.
They're very common. And if you wear sunglasses a lot of times, you can see them. I want you to be careful when you look toward the sun, but you know, whenever I walk out of a building, I always put my hand up and block the sun and put my sunglasses on and look around the sun because often you'll see coronas.
Okay, and now Vivek, of course, is also saying it's a fascinating talk, just like Ri said, but he says, how would you differentiate if what you're seeing is actually something out there in nature versus some things like lens flare or, you know, so how can you be sure that what you're seeing is something that is not an artifact of the system?
Yeah, it's a good question. I think the answer is that, first of all, once you become familiar with what the options are, with what the theory predicts, you know, I understand that there should be a rainbow and there should be a primary and a secondary.
Yeah.
There is a third order rainbow, but you have to look in the wrong direction. And so once you understand where to look and what to look for, you can recognize them very quickly. But lens flare is indeed a problem because a lot of times we're taking pictures with the sun in the field of view. I guess my recommendation would be, if I ever have any doubts, I just put my hand out and block the sun in front of my lens, or use a street light or something or a tree to block the sun. And I think I learned that. Didn't you write a paper, Yoav, talking about the geometry of lens flare?
Yes, I agree. But Vivek was asking you, so I wasn't.
Yeah. And so there's a very specific geometry where the flare should be, and if it's not there, then it's not likely to be a lens flare. So that's another thing.
Yeah. So I think one of the answers to the question, and that's giving the rest to my question, is the issue of taking sequences of images over time, because on one hand that can decouple things that are out there in nature that are static versus your sensor that may be moving or something like that. On the other hand, all your examples are of static effects. And I wanted to ask you about effects that arise from dynamics. It can be the dynamics not of the light, it can be the dynamics of, so for example, you talked about the wiggling or something, right? So if you take some exposure and during this exposure, there's something that you can learn something about the dynamics of the scene rather than on the spatial things in the scene. And also, do you consider expanding your work towards short sequences or long sequences that would teach us something about nature and give us more illuminating examples?
I think that's a great question. One example comes to mind is when we were on FLIP, that floating instrument platform, inverted ship, we also had a glint imager and we recorded video. Now, this is the 1990s, so I was recording video on VHS tape and processing them for five minutes of video would take many hours to process. Nowadays, we could do it easily, but those videos of the glint patterns, I think, contain a lot of information about the dynamics of the ocean surface. And I actually have a proposal in right now to revisit that project, but with modern digital imaging technology, because I think there's a lot of dynamics that you can uncover. The other thing is, I didn't talk about auroras in this talk, but I love aurora photography. I grew up in Alaska, as Yoav knows, and so I think it's my favorite optical phenomenon is the aurora, and it's very dynamic. And to really learn from those dynamics, though, you really have to understand more about solar physics than I really understand. But I think that's an example of having the dynamic images contain a lot of information about the dynamic physics.
Okay, I hope the broadcasting people will allow me to squeeze in one more question because I'm really curious. So, did you or your colleagues in the community think about generalizing that kind of work to hypothesize what would be seen in other other bodies in the solar system? I don't know, in Venus they have sulfuric acid droplets, in Jupiter they have ammonium ice. So they would have not only different refractive indices, they may have different crystal structures when they're ice, so maybe they're not hexagonal, I don't know. So that would give different kind of halos, different kind of methane, rainbows, etc. Is there work done in trying to hypothesize these effects there, again considering wind there and wobbling there, etc.?
Absolutely, there is. Some of the people in our community come from astronomy backgrounds, and those people especially are likely to be doing this. And so there have been some really, I've never done any of that work myself, but some of the names that I can think of are David Lynch, L-Y-N-C-H.
Yeah.
Dave Lynch has done some of this. Gunther Koenen up in Holland has done some of this. Franz Snick recently has been doing a lot of work with looking at polarization of, there's several groups in the world that are theorizing that might be a great way to detect planets with life on them, is to look for a polarization signature related to water. And so there have been a number of papers published about what kind of rainbows and halos might exist on Venus or different planets, given what we know about their atmospheres. And those are fascinating things. I've even seen a couple papers that show images from, we're starting to get lots of really high quality digital images from space probes. And there have been some, gosh, I can't remember now who published that, but I saw a paper that was talking about, can't remember if it was halos or rainbows on one of the other planets, but I can't even remember what it was. But yes, these papers are out there and they're just great.
Great. Thank you very much. I think this is a really, really fun talk. I believe people will visit this video and we look at it. Thank you very much, Joey.
Thank you for inviting me, Yoav. It's my pleasure to be here.